In the quiet reaches of the constellation Serpens, some 250 million light-years from Earth, lies one of the most violently beautiful cosmic phenomena ever recorded. It doesn't look like much to the naked eye, not even to most visible light telescopes. But beneath its dusty veil, this object burns with the ferocity of 1,000 galaxies. This is ARP 220, a place where stars are born faster than fire spreads through a dry forest, where supernovae explode in rapid succession like cosmic fireworks, and where the very bones of two spiral galaxies are being crushed, melted, and reforged into something altogether new and strange. But before we continue, subscribe to the channel and like the video. ARP 220 is more than just a galaxy. It is a collision in progress, a fiery, churning monument to one of the most powerful forces in the universe, galactic merger. But this is no ordinary merger. ARP 220 is what astronomers classify as a ULIRG, an ultraluminous infrared galaxy. That alone makes it rare. But what makes it truly astounding is its core, where more than 200 supernova remnants, the dead, glowing shells of exploded massive stars, are packed together in one compact region. No other known galaxy in our cosmic neighborhood even comes close. To look at ARP 220 is to witness nature at its most extreme. It is a living laboratory of heat, dust, gravity, and time. It is a place where stars are born and die in rapid-fire succession, where gravity has twisted the very fabric of structure and balance, and where the universe tells one of its most dramatic stories, that of death, rebirth, and transformation on a galactic scale. But this story didn't begin recently. The chaos we observe now is the aftermath of a long and catastrophic romance. Two spiral galaxies, once peaceful and full of order, slowly drawn together by mutual gravitational attraction. Over hundreds of millions of years, these galaxies spiraled toward one another, their arms distorted, their stars flung into new orbits, their gas clouds compressed and ignited. What remains now is a single entity, a warped, unstable behemoth undergoing such rapid internal evolution that astronomers sometimes call it a cosmic furnace. What makes ARP 220 even more captivating is how hidden it is. To optical telescopes, it's a murky blob, its brilliant heart cloaked by thick clouds of interstellar dust. But through the lenses of infrared and radio astronomy, its true nature is revealed. It blazes with a brightness thousands of times more intense than the Milky Way, but almost all that light is in the infrared. This is no gentle galaxy drifting quietly through space. It is a violently bright, supremely energetic storm of starbirth, death, and nuclear activity. And that's just the beginning. In this 3-hour-long exploration, we're going to peel back every layer of ARP 220. We'll uncover how it formed, what it is, why it glows so brightly in the infrared, and how it's become a factory of supernovae. We'll dive into its dual nuclei, its potential black holes, its molecular chaos, and what it can tell us about the ultimate fate of galaxies, perhaps even our own Milky Way. Because ARP 220 isn't just an object of curiosity. It's a preview, a glimpse into what happens when massive galaxies collide. A portrait of transformation painted in stars, dust, and gas. It is one of the most active, mysterious, and violent regions of the nearby universe, and it's still evolving. Let's begin the journey by understanding what exactly this monster is. Nestled in the constellation Serpens, about 250 million light-years from Earth, lies a galaxy that doesn't just shimmer, it roars. This is ARP 220, and while it may appear as a faint smudge in visible light, its true form is anything but subtle. It is one of the most luminous galaxies in the nearby universe, a fact that only becomes apparent when you stop trying to see it with human eyes and start listening to the light it emits beyond the visible spectrum. ARP 220 belongs to a rare and dramatic class of galaxies known as ULIRGs, Ultraluminous Infrared Galaxies. That classification alone says something crucial. While most galaxies shine primarily in visible light, ARP 220 radiates almost all of its energy in the infrared. And it's not a gentle glow, it's intense, chaotic, and nearly unmatched in our cosmic neighborhood. The entire galaxy is bursting with energy that's been absorbed by thick clouds of interstellar dust and re-radiated at longer wavelengths, invisible to our eyes but astonishingly bright in infrared detectors. It resides in a region of sky that appears calm and unassuming, but that contrast only heightens the drama. Serpens, the constellation that cradles this galactic inferno, is relatively quiet compared to other deep sky hunting grounds like Orion or Virgo. Yet, embedded within it is this cosmic furnace, a hidden epicenter of galactic violence and rebirth, so far away that even light, moving at 300,000 kilometers per second, takes 250 million years to reach us. That's right, when we observe ULIRG 220, we are seeing it as it was 250 million years ago. Dinosaurs hadn't even begun to walk the Earth when the light we now detect first began its journey. And in that time, the story of ULIRG 220 has only grown more compelling. To understand what makes this galaxy so important to astronomers, it helps to understand what it's not. ULIRG 220 is not a spiral galaxy, not an elliptical, not even a lenticular. It is a chaotic hybrid, formed from destruction, shaped by violence, and fueled by the kind of cosmic events that redefine structure on a galactic scale. It is an object that defies classification by traditional means because its formation is still in progress. This is a galaxy in transition, a moment frozen in time during one of the universe's most transformative processes. Observing ULIRG 220 is like catching a star mid-supernova, rare, fleeting, and packed with valuable information. It offers clues not just about itself, but about galaxy evolution as a whole, and by extension, about the ultimate fate of galaxies like our own. It is also extremely compact for its brightness. While it holds the luminosity of hundreds of billions of suns, all that energy is packed into a space much smaller than the Milky Way. The central kiloparsec, about 3,200 light-years across, is where most of the action happens. Inside this relatively tiny volume, ULIRG 220 compresses a staggering amount of mass, dust, and radiation. That sheer density is part of what fuels its chaotic nature, creating a feedback loop of star formation, dust absorption, infrared emission, and stellar death. ULIRG 220 was catalogued by Halton Arp in his famous Atlas of Peculiar Galaxies, where it was noted not for its symmetry or grace, but for its strangeness. Arp had a fascination with galactic anomalies, objects that didn't fit neatly into any established classification. ULIRG 220 certainly earned its place on that list, and since then, it has become an icon of galactic upheaval. What makes it so special, so worthy of attention, is that it's not just a curiosity, it's a prototype for understanding how galaxies interact, merge, and evolve. Even now, long after its discovery, astronomers continue to turn their most powerful telescopes toward this cosmic conflagration. From ground-based observatories to spaceborne giants like the James Webb Space Telescope, ULIRG 220 remains a focal point for cutting-edge research. And every new image, every new data set, reveals more layers to its extraordinary story. To understand the true nature of ULIRG 220, we need to unpack what it means to be a ULIRG, an ultraluminous infrared galaxy. These aren't your everyday galaxies. They are cosmic outliers, rarities in the nearby universe, and they burn with an intensity that defies expectations. What makes them particularly fascinating is how they choose to shine, not in visible light, the kind our eyes are tuned to detect, but in the infrared. Their brilliance is not seen, it's felt, revealed only when we peer through the invisible spectrum of heat and dust. The term, ultraluminous, isn't just poetic, it's precise. To be classified as a ULIRG, a galaxy must emit more than 1 trillion times the luminosity of our Sun, in the infrared alone. That's more than 100 times the infrared luminosity of the Milky Way. Only the most extreme environments in the universe reach these levels of output, and they are nearly always linked to something cataclysmic, major mergers, ferocious starbursts, or active galactic nuclei deeply buried in gas and dust. The driving force behind this infrared radiance is dust, but not the kind you brush off a bookshelf. Interstellar dust in galaxies like ULIRG 220 is made of tiny solid particles, carbon, silicates, ices, suspended in gas and scattered across the galaxy. In normal galaxies, dust is present but manageable. In ULIRGs, it becomes overwhelming, coating the entire central regions in a thick, impenetrable fog. When stars form, especially massive ones, they release an enormous amount of energy in ultraviolet and visible light. But in galaxies like ARP-220, those wavelengths don't get very far. They are immediately absorbed by the dust, which heats up as a result. Then the dust itself re-radiates that absorbed energy, but it does so at much longer wavelengths, in the infrared part of the spectrum. So while an optical telescope might see only a dim blotch, an infrared detector reveals a searingly bright object, an object glowing not with starlight, but with the heat of creation. This is why ULIRGs are often called infrared beacons. They punch through the darkness of space not by shining invisible light, but by glowing in the wavelengths most closely associated with warmth and heat. In essence, they are telling us, here is where the action is. Here is where stars are being forged in extraordinary numbers. These galaxies are rare in the local universe. Only a few dozen have been found within a few 100 million light-years of Earth. But when we look deeper into space, and thus further back in time, we find that ULIRGs were far more common in the early universe. That's no coincidence. The early universe was more chaotic, more collision-prone, and more gas-rich, exactly the conditions that fueled the kind of intense starbursts that make a galaxy go ultraluminous. ARP-220, then, is not just a modern marvel, it's a fossil echo, a rare nearby example of processes that once shaped the universe on a massive scale. And there's more. ULIRGs don't just shine brightly, they hide secrets. Many of them, including ARP-220, may contain active galactic nuclei, or AGN, buried under thick layers of gas and dust. These are supermassive black holes that are feeding on surrounding material, releasing vast amounts of energy in the process. But because the light they produce is shrouded in dust, we can't always see them directly. Instead, we infer their presence through the spectrum of radiation that escapes, through the motion of gas near the center, or through high-energy signatures in X-rays and radio waves. This makes ULIRGs like ARP-220 multi-layered mysteries. They are not just places where stars are forming, they are places where matter is being torn apart, where energy is being trapped and re-emitted, and where the line between creation and destruction is blurred. Every observation, every new image, reveals something new, a dense knot of molecular gas here, a stream of colliding stars there, an unexpected outburst of radio emission from deep within the core. ARP-220, as a ULIRG, is the most intense, compact, and complex example we've found close to home. It embodies everything that defines the class: the massive dust content, the staggering star formation rate, the hidden cores, the immense luminosity, and the sense of constant, unstoppable change. It is both a laboratory and a paradox, immensely bright, yet mostly invisible, incredibly active, yet nearly opaque to our eyes. Before ARP-220 became the blazing furnace of stars that it is today, it began as something much more familiar: two spiral galaxies, possibly similar to our own Milky Way. For billions of years, each of these spirals evolved independently, spinning serenely through space with their own stars, gas clouds, dust lanes, and central bulges. They may have hosted star-forming regions in their spiral arms, perhaps even had planets circling quietly in orbit around their stars. But fate had other plans. Drawn together by mutual gravitational attraction, the two galaxies began a slow and deadly dance, one that would eventually reshape them completely. Galactic collisions are not rare on cosmic timescales, but what makes ARP-220 stand out is the timing. We've caught it right in the middle of this process, after the collision has torn apart the original structures, but before full stabilization has occurred. It's like witnessing the climax of a movie without knowing how it ends. When galaxies merge, the stars themselves don't usually collide. They are too far apart for that. But gas and dust are a different story. As the galaxies spiral inward toward each other, gravitational forces warp their shapes, stretching spiral arms into long tidal tails, pulling stars and gas into chaotic orbits, and funneling massive amounts of interstellar material into the core. And that's where the real chaos begins. In the case of ARP-220, this inward surge of gas has created an extraordinary scenario. Instead of dissipating or spreading out, much of the gas from both parent galaxies was driven into a hyperdense central region, compressing into a volume just a few thousand light-years across. The pressure and density became so high that it triggered one of the most powerful starbursts ever observed in a nearby galaxy. What once were two elegant spirals now form a twisted, compact object overwhelmed by its own activity. Their original shapes are barely discernible, scrambled beyond recognition. Where there were once distinct spiral arms and well-separated centers, there is now a messy, whirling structure dominated by intense gravitational interactions, wild gas dynamics, and regions of furious star formation. In deep images, one can still trace the faint hints of tidal tails, those long streams of stars flung outward by the violence of the merger. These tails are the fingerprints of the original galaxies, like the shredded fabric of their former elegance being stretched thin and scattered across the sky. They serve as evidence of the gravitational forces at play and help astronomers reconstruct how the merger unfolded. The process of a galactic merger like this is anything but quick. Though it might seem explosive, it plays out over hundreds of millions of years. ARP 220 is in a particularly advanced stage of this process, what astronomers call a late-stage merger. The central regions have already coalesced, but the effects of the collision still ripple outward. The system is compact now, but its gravitational equilibrium is far from settled. One of the most intriguing features of this scenario is that both original galactic cores have survived the initial collision. Rather than immediately fusing into one, the nuclei of the parent galaxies remain distinct, visible today as a pair of closely spaced energy sources, embedded deep within the dust of ARP 220's core. These are not just symbolic leftovers. They are active regions, each surrounded by dense clusters of young stars, supernova remnants, and possibly even their own central black holes. Their proximity, only about 1,200 light-years apart, indicates that they are in the final stages of merging, spiraling slowly toward an eventual union. As these two cores orbit each other, they distort the surrounding gas, triggering massive shockwaves and compressing material into dense clumps. These clumps, in turn, give birth to new stars at a pace that dwarfs almost any other known system in the local universe. The galaxies that once had their own stable rhythms have been thrown into complete disarray, and yet from this chaos, a new form is emerging. We are watching, in real time, a transformation that has likely played out billions of times across the universe's history, but rarely with this much detail, and rarely this close to home. ARP 220 is a window into a fundamental process of cosmic evolution, the building of larger, more complex galaxies through the destruction and assimilation of smaller ones. Eventually, the two nuclei will fully merge. Their stars will intermix, their black holes may collide, and a new, more stable galaxy will emerge from the wreckage, probably a giant elliptical, the kind we see in older, more settled galactic environments. But that final form is still in the future. Right now, ARP 220 is a system in transition, a churning maelstrom of heat, dust, gravity, and raw creation. It is a galaxy being born from the ruins of its ancestors. There's a poetic quality to this tale of two galaxies. It's a story of unity through destruction, of birth through violence. It reflects one of the most consistent truths in astronomy, that creation and annihilation often go hand in hand. Galaxies are not eternal, immutable structures. They grow, evolve, interact, and change, shaped by time, by motion, and by the constant tug of gravity. ARP 220 reminds us that nothing in the cosmos stands still. Even galaxies, those mighty islands of stars that span hundreds of thousands of light years, are subject to the same cosmic forces that shape everything else. They collide. They transform. They survive, not as what they were, but as something altogether new. In the aftermath of ARP 220's cataclysmic collision, the galaxy has become a crucible of extraordinary transformation. When two spiral galaxies collide, the gravitational forces involved don't just tangle stars and fling them into new orbits. They wreak havoc on the invisible scaffolding of gas and dust that underlies star formation. In the case of ARP 220, this collision was so thorough, so relentless, that it forced nearly all the interstellar material from both galaxies into a small central region. The result? A detonation of star formation on a scale rarely seen in the nearby universe. The raw ingredients of this event, cold molecular gas, interstellar dust, and turbulent pressure, were not lost or dispersed in the chaos. Instead, they were pulled inward by the immense gravitational center created during the merger. Gas that once flowed peacefully in spiral arms now spirals violently into the heart of the newly forming galaxy. And it is this central congestion of gas, concentrated and compressed, that acts as the fuel for a spectacular starburst. In ARP 220, the density of gas in the central kiloparsec is off the charts. The galaxy holds an estimated 10 billion solar masses of molecular gas concentrated in that compact region, a staggering amount, and more than enough to fuel generations of stellar creation. In fact, the core is so choked with gas and dust that it blocks nearly all visible light from escaping. This opacity makes it impossible to observe the starburst directly with optical telescopes, but observations in infrared, submillimeter, and radio wavelengths reveal the furnace beneath the veil. What's taking place in that furnace is nothing short of phenomenal. ARP 220 is producing new stars at a rate of 100 to 1,000 times that of the Milky Way. To put that into perspective, our galaxy gives birth to about 1 solar mass star per year on average. ARP 220, by contrast, is generating hundreds of them annually, many of them far more massive than our Sun. And because massive stars have much shorter lifespans, living only a few million years before exploding as supernovae, ARP 220's core is in a perpetual state of both birth and death. Stars are being created, living short, violent lives, and then detonating in titanic explosions that compress more gas and trigger more star formation. This runaway cycle is part of what defines a starburst galaxy, and in ARP 220, it is amplified to an extreme. Observations have shown that a majority of the galaxy's infrared luminosity comes from the central few hundred light-years, a region where the energy output per unit volume rivals that of an entire normal galaxy. It's a pressure cooker of physics, where every element is being driven to its limit. As gas pours inward, it doesn't settle gently. The material is so turbulent and densely packed that shockwaves, magnetic fields, and rotational shear twist it into complex filaments and clumps. These structures are highly unstable and collapse rapidly under their own gravity, birthing dense stellar clusters, compact groups containing thousands or even tens of thousands of young, massive stars. These are not like the open clusters we see in our galaxy, where stars are loosely bound and easily dispersed. These are tightly packed, gravitationally robust, and born in the chaos of the collision. But not all of the gas ends up forming stars. Some is heated by radiation pressure, blown away by stellar winds, or expelled by supernova explosions, adding further complexity to the central environment. The interplay between gas inflow, star formation, and feedback from young stars creates a turbulent ecosystem where every process influences the next. It's a feedback loop of creation and destruction, with ARP 220 acting as both incubator and executioner. One of the consequences of this intense central starburst is the rise in infrared luminosity. The young, massive stars emit ultraviolet and visible light, but as that radiation is absorbed by the surrounding dust, it heats the dust particles and causes them to glow brightly in the infrared. That's why ARP 220 is such a brilliant object in that spectrum. It's not just bright, it's ultraluminous, radiating over 1 trillion times the energy of the Sun, most of it in the form of thermal infrared emission from warm dust particles. The sheer rate at which stars are forming and dying means that the galaxy is filled with supernova activity, a phenomenon we'll explore in depth later. For now, it's enough to understand that the central region of ARP 220 is one of the most active and violent star-forming zones in the known universe. It is the outcome of a perfect storm, a massive influx of gas, a complete structural disruption, and an environment so extreme that it bends the normal rules of galactic evolution. And it doesn't stop there. The energy released by this starburst is so immense that it affects the very structure of the galaxy. Outflows of gas have been detected shooting away from the center, driven by the cumulative force of stellar winds, radiation, and supernova explosions. These winds can carry enriched material, elements like carbon, oxygen, and iron, out into the galaxy's halo and even into intergalactic space. This is the process of cosmic recycling, where the products of stellar evolution are ejected and later reused in new generations of stars and planets. There's another layer to all this. As the central starburst continues to rage, It likely obscures the presence of supermassive black holes, which we suspect are nestled within the two galactic nuclei. These hidden giants may be accreting matter as well, contributing their own energy to the overall luminosity. But the dust is so thick, and the starbursts so dominant, that any signs of active galactic nuclei are effectively drowned out, at least for now. ARP 220 is the ultimate example of what happens when galaxies collide with enough mass, gas, and violence to trigger sustained star formation at absurdly high levels. Its current state is not permanent. Such intense activity is unsustainable over long timescales. Eventually, the gas will run out or be blown away. The starburst will fade. The glowing infrared light will dim. But for now, we are witnessing a rare, short-lived phase in galactic evolution, one where the volume of space is so alive with activity that it's almost beyond comprehension. In the hierarchy of galactic behavior, most galaxies are relatively calm. Even those actively forming stars do so at a modest pace, converting clouds of gas into stellar nurseries over millions of years. The Milky Way, for example, forms about 1 or 2 new stars per year. But then there are galaxies like ARP 220, galaxies that burn like a wildfire instead of simmering like a campfire. These are known as starburst galaxies, and ARP 220 is one of the most extreme cases known in the nearby universe. What defines a starburst galaxy is not just the rate of star formation, but also the efficiency and density with which it occurs. In ARP 220, this process is happening at hundreds of times the rate of the Milky Way, but within a region only a tiny fraction of its size. Imagine compressing all the star-forming activity of an entire galaxy into a volume only a few thousand light-years across. That's the heart of ARP 220, a galactic forge that pushes the limits of what star formation can be. The term, starburst, refers to a short-lived but intense period of stellar production. These bursts are typically triggered by some violent event, most often, a galactic merger, that funnels massive quantities of gas into the central regions. The resulting compression causes interstellar clouds to collapse under their own gravity, triggering the rapid birth of new stars. The process feeds on itself. Massive stars heat and stir their surroundings, shockwaves from supernovae compress additional gas, and entire clusters of stars form in succession like falling dominoes. In ARP 220, this chain reaction is running on overdrive. Observations suggest that between 50 and 100 new stars are born every year, and many of these are not low-mass stars like the Sun, but high-mass giants that live fast and die young. These massive stars emit fierce radiation, eject powerful winds, and eventually explode as supernovae, all within a few million years of their birth. That's why ARP 220 is not only a starburst galaxy but also a supernova factory, something we'll explore more deeply in the next sections. What makes ARP 220 particularly remarkable is how localized its starburst is. The vast majority of this furious activity is confined to the inner kiloparsec, just 3,200 light-years across. To put that in perspective, the Milky Way is over 100,000 light-years wide. Yet within this small region, ARP 220 is producing more energy than our entire galaxy. The compactness of the activity is one of the reasons why the core is so heavily dust-enshrouded. All of the radiation, energy, and material from these newly forming stars gets trapped in a confined space, making the region incredibly hot, bright in the infrared, and opaque to visible light. Another hallmark of ARP 220 starburst nature is the presence of young superstar clusters, massive groups of stars born together in tightly packed regions. These clusters often contain tens of thousands of stars and are among the most luminous and dense stellar systems known. They are thought to be precursors to globular clusters, which we see as ancient relics in the halos of galaxies today. In ARP 220, these clusters are being born not as a slow drizzle over billions of years, but as a sudden downpour. This high-efficiency formation is made possible by the sheer abundance of molecular hydrogen, the raw material for star formation. Observations using instruments like ALMA, ATACMS, a large millimeter/submillimeter array, revealed dense knots of cold molecular gas within the central core, some with masses of over 1 million suns. These gas reservoirs are like galactic powder kegs. Once they reach a critical point of pressure and temperature, they ignite the birth of massive clusters at a furious pace. But this kind of stellar production comes at a cost. Starbursts, especially ones as intense as ARP 220s, are unsustainable. The gas supply is finite, and the feedback from young stars, winds, radiation pressure, and supernovae begins to heat, blow away, or ionize the surrounding material. In effect, the galaxy begins to choke on its own fire. Over time, these feedback processes slow down or shut off further star formation, and the starburst phase fades into memory. Most models suggest that ARP 220 starburst cannot last more than a few 100 million years at most. That brevity, however, is part of what makes it so compelling. To catch a galaxy in the starburst phase is to witness cosmic adolescence, a moment of wild, rapid change before the system settles into a more stable, mature state. And unlike many distant ULIRGs whose details are lost to the limits of our telescopes, ARP 220 is close enough that we can observe this process in unprecedented detail. There's a deeper implication here, too. Galaxies like ARP 220 serve as analogs for conditions in the early universe, when gas was more plentiful and mergers more common. Back then, starburst galaxies were the norm rather than the exception. The intense star formation we see in ARP 220 might have been typical in the cosmos 10 billion years ago. In that sense, ARP 220 is both an active system and a time machine, showing us what galaxies used to be like during one of the most productive eras in cosmic history. Starburst galaxies also play a crucial role in chemical enrichment. Massive stars formed in these environments die quickly, spewing out elements like carbon, nitrogen, oxygen, and iron into the interstellar medium. These elements are the building blocks of planets, life, and even human bodies. Every breath we take carries atoms forged in ancient supernovae. So when we look at a galaxy like ARP 220, we're also witnessing the seeding of future cosmic generations, a chain reaction that will echo for billions of years. The violence, the pressure, the radiance, these are the traits of ARP 220 in the throes of a cosmic fever. It is not a peaceful place. But it is a productive one, and in the story of the universe, such places are pivotal. They mark the turning points, the periods of rapid transformation that shape the galaxies we see today. ARP 220 starburst isn't just an astronomical curiosity, it's a crucible. And in that crucible, the universe is forging the raw materials for the next act of cosmic evolution. To truly grasp the nature of ARP 220, you have to step beyond the visible. Look at it through a standard optical telescope, and you'll see what looks like a dull, reddish smudge, a ghost of a galaxy, shrouded and shapeless. But switch to the infrared, and suddenly that smudge becomes a blazing beacon. In the infrared spectrum, ARP 220 is a cosmic inferno, burning with the energy of over 1 trillion suns. That's not hyperbole. ARP 220 is so bright in infrared light that, in terms of total energy output, it rivals or surpasses entire clusters of galaxies. But this brilliance isn't because the galaxy is particularly filled with more stars than others, it's because of how it emits its light. Almost every photon of visible and ultraviolet light produced by ARP 220's young, massive stars is absorbed by the thick clouds of dust that envelope its core. This dust acts like a heavy blanket, soaking up starlight and heating up in the process. But energy doesn't just disappear. Once heated, the dust re-radiates that energy at much longer wavelengths, specifically in the infrared. And so, while ARP 220 may seem faint or obscured in the visible spectrum, it blazes with overwhelming power in the infrared. It doesn't just glow, it dominates. Observed at wavelengths of 60, 100, or 160 microns, ARP 220 outshines virtually every galaxy in its vicinity. That's why it was first flagged by infrared space telescopes like IRAS, Infrared Astronomical Satellite, in the 1980s. To instruments tuned for the heat of dust rather than the glow of stars, ARP 220 was practically screaming. But why is there so much dust in the first place? The answer lies in the galaxy's violent past, and its even more violent present. The merger of two spiral galaxies didn't just bring stars together. It brought together their gas and dust reservoirs, funneling them into the galactic center and increasing densities dramatically. Then, as the starburst phase ignited, it began producing massive stars at breakneck speed. These stars, with their fierce winds and short lifespans, generated even more dust through their deaths. Supernovae spewed heavy elements into space, which cooled, condensed, and added to the dust budget. So what you end up with is a feedback loop. Dust triggers star formation leads to massive stars produce more dust, and the whole process keeps intensifying until the galaxy becomes choked with its own productivity. In ARC 220, this cycle has been running for at least 100 million years, maybe longer, and the result is a galaxy that has become almost completely opaque to visible light. To see through this opacity, astronomers use instruments designed to detect far-infrared and sub-millimeter radiation. Space telescopes like Spitzer, Herschel, and now JWST, along with ground-based arrays like ALMA, have revealed the hidden structure of ARC 220's glowing heart. What they found is staggering: compact star-forming regions where temperatures soar, dust glows at over 100 Kelvin, and energy densities rival those at the centers of active galactic nuclei. And it's not just the quantity of light that's remarkable, it's the efficiency. ARC 220 converts gas into stars so rapidly, and the surrounding dust is so good at capturing and re-emitting energy, that the system operates near what physicists call the Eddington limit. This is a theoretical maximum beyond which radiation pressure would become so strong that it starts blowing material away from the galaxy's center. ARC 220 is brushing up against that limit, an astronomical balancing act between gravitational collapse and explosive energy output. The galaxy's spectral energy distribution, SED, is overwhelmingly skewed toward the infrared. Over 99% of its total energy emerges at wavelengths longer than a few microns. This makes ARC 220 a textbook example of how dusty starburst galaxies hide their power behind cloaks of gas. In fact, if it weren't for infrared observations, ARC 220 might have seemed like just another faint, unremarkable galaxy in an obscure part of the sky. Instead, it's known as the nearest ULIRG and one of the most intensely luminous galaxies in the local universe. This extreme luminosity has practical implications. It means that ARC 220 can be detected across vast distances, not by its visible light, but by its infrared glow. And because this glow is so intense, it acts like a cosmic lighthouse, helping astronomers identify and study similar objects at much greater distances. Many of the most distant galaxies ever observed are ULIRG-like systems that existed in the early universe. In studying ARC 220, we get a close-up view of what those early galaxies might have looked like, how they might have behaved, and how their light pierced the fog of cosmic time. There's also the question of energy sources. Could all this light really be from star formation alone? Or is there something else hiding in the dust? Some researchers suspect that supermassive black holes, one in each galactic nucleus, might be contributing to ARC 220's luminosity. But so far, there's no clear, unambiguous signature of an active galactic nucleus, AGN. If black holes are indeed accreting matter in the core, they're completely buried beneath hundreds of solar masses worth of gas and dust. This raises an intriguing possibility, that ARC 220 may be a composite galaxy, with both extreme star formation and buried AGN activity contributing to its output. But without direct evidence, we can only guess. What we do know is that the infrared output is dominated by thermal radiation from heated dust that owes its temperature to thousands of blazing young stars packed tightly into the galaxy's dense core. It's this hidden fire, this trapped starlight re-emerging as infrared heat, that makes ARC 220 so fascinating. It's not just a bright galaxy, it's a galaxy transformed by its own light, a place where photons are born, buried, and then reborn again at longer wavelengths. In a universe where most galaxies wear their light on their sleeves, ARC 220 holds it close, deep within a furnace that can only be seen by peeling back the veil with the right instruments. And in doing so, it reminds us that the cosmos doesn't always reveal its secrets openly. Sometimes, the most dazzling fireworks are hidden in the shadows, shining brightest only when we learn to see in the dark. At the heart of ARC 220 lies a region so thoroughly smothered in interstellar dust that visible light is rendered virtually useless. This dusty core is the engine room of the galaxy, the source of its furious energy, and a hiding place for some of the most extreme astrophysical processes in the nearby universe. But it's also nearly invisible to traditional telescopes, a cloaked inferno, emitting almost nothing in the wavelengths that human eyes, or even the world's best optical observatories, can detect. Dust in galaxies isn't like the dust we find on a shelf or in a room. It's made up of microscopic grains, mostly carbonaceous compounds, silicates, and icy particles, each no more than a fraction of a micron in size. Yet collectively, this dust has an enormous impact. It absorbs ultraviolet and visible light with great efficiency, especially in regions where it's densely packed, like the core of a starburst galaxy. And ARC-220 has dust in industrial quantities. The central region, extending just a few hundred light-years across, is so densely packed with gas and dust that it blocks more than 99% of all visible light. Even powerful instruments like the Hubble Space Telescope can barely detect the faintest glimmer through the obscuring veil. What Hubble sees is a fuzzy, mottled structure, ambiguous and unclear. It's like trying to see the heart of a volcano through smoke and ash. We know something powerful is happening beneath, but the direct light can't get out. That's why astronomers turn to infrared and radio wavelengths, the longer forms of light that can slip through the dust. Infrared light is emitted by warm dust particles themselves, and radio waves are so long they pass straight through even thick clouds. These two bands are our windows into ARC-220's hidden furnace, and without them, we'd be effectively blind to the galaxy's true nature. Infrared observations, especially from missions like Spitzer, Herschel, and now the James Webb Space Telescope, have revealed a glowing, thermally radiant core. The dust in this region is not cold and passive, it's hot, heated by intense ultraviolet radiation from massive stars forming in the region at a breakneck pace. Temperatures of the dust reach between 50 and 100 Kelvin, far above the cosmic background, and in some dense knots near the nuclei, even higher. This warm dust radiates powerfully in the mid and far infrared, which is exactly where ARC-220 emits most of its energy. But it's the radio that really cuts to the core. High-resolution observations using interferometers, arrays of linked radio telescopes like the Very Large Array, VLA, or ALMA, have peered through the dust to detect the activity within. These instruments have mapped out the galaxy's double nuclei, tracked jets of molecular gas, and most astonishingly, revealed the presence of over 200 compact radio sources within the central few hundred light-years. These sources are believed to be supernova remnants, the remains of massive stars that have exploded in recent times. In the visible, these explosions would be brilliant beacons. In ARC-220, they are radio ghosts, shining only for those who know how to listen. The presence of so much dust also affects the dynamics of the galaxy. Dust is not just an obstacle to observation, it is a driver of galactic processes. It contributes to the overall mass in the core, affects gravitational potential, helps regulate the temperature and pressure of the interstellar medium, and serves as a surface for key chemical reactions. Molecules like H2, CO, and more complex organics often form on the surfaces of dust grains. These molecules, in turn, shape the thermodynamic state of the gas and influence where and how stars form. The high dust density also creates enormous radiation pressure. As light tries to escape from the starburst regions, it pushes against the dust, sometimes with enough force to drive outflows of material from the core. These dusty winds carry metals and enriched gas away from the galactic center, distributing it throughout the galaxy and even into intergalactic space. It's a kind of cosmic respiration, inhaling gas in the form of inflows from the merger, and exhaling energy and material through starburst-driven winds. There's a mysterious side to all of this, too. Because dust is so effective at concealing what lies beneath, it raises the tantalizing possibility that even more extreme phenomena are hidden within. Many astronomers suspect that ARC-220's nuclei might harbor supermassive black holes, accreting gas and potentially powering low-luminosity active galactic nuclei, AGN. If so, they are completely invisible in the optical and only hinted at through subtle features in the infrared and radio. In fact, some X-ray observations have hinted at hard X-ray sources in the core, signatures that could be from AGN, but the dust is so thick that even high-energy X-rays are partially absorbed. It's rare to find a galaxy where dust absorption is so severe that it effectively hides the X-ray output of a black hole, but ARC-220 may be just that unique. This is why ongoing multi-wavelength studies are so crucial. Every new frequency band peels away another layer of this cosmic onion. The obscuration isn't evenly distributed either. The dust forms complex structures, disks, clumps, filaments, each with different temperatures and densities. Advanced modeling, using data from multiple observatories, shows that there are likely several distinct dust components, ranging from cooler, diffuse material on the outskirts to hot, dense knots near the twin nuclei. Understanding how these regions connect is vital to reconstructing the galaxy's internal structure and evolution. Yet, despite the opacity, the data continues to flow. With ALMA's exquisite resolution, astronomers have traced the rotation of molecular gas in the core, revealing turbulent disks of material spinning around the two galactic nuclei. These disks are not aligned, they're tilted, twisted, and colliding, adding further chaos to the region. The dust here acts as both a barrier and a storyteller, blocking the light but shaping the thermal and dynamic history of ARC-220's violent transformation. In a way, the dusty core of ARC-220 is like the nucleus of a storm. It's where the pressure is highest, the energy most concentrated, and the processes most extreme. And yet it's also the most shielded, the most hidden from view. It challenges our instruments, our models, and our patience. But in overcoming these challenges, astronomers gain not just a better understanding of one galaxy, but of many. Because ARC-220 is not alone. There are others like it, farther away, more obscured, more extreme. By decoding ARC-220's dusty veil, we're laying the groundwork for understanding the hidden engines of the cosmos at large. Buried deep within the churning, dust-cloaked heart of ARC-220 lies one of the most telling signs of its violent history. Two galactic nuclei, still distinct, still recognizable, and still orbiting each other in a gravitational dance that began hundreds of millions of years ago. These nuclei, separated by only about 1,200 light-years, are not just leftovers from the two spiral galaxies that merged. They are active hubs of star formation, molecular chaos, and possibly black hole activity, all crammed into a volume smaller than the width of our own Milky Way's central bulge. To the naked eye or even the lens of most visible light telescopes, these nuclei are invisible. Hidden behind thick curtains of interstellar dust, they would remain unknown to us if not for radio and submillimeter observations, especially those from instruments like the Atacama Large Millimeter/Submillimeter Array, ALMA, and the Very Large Array, VLA. These observatories have been able to peer through the cosmic fog, tracing out the positions, motions, and compositions of these compact structures with stunning precision. Each nucleus is like a mini-galaxy in its own right, still holding on to its original structure, and surrounded by swirling disks of gas and stars. In other mergers, galactic cores often coalesce quickly, erasing all signs of their dual identity. But in ARC-220, the process has slowed, stalled by the enormous gravitational inertia of the system and by the incredible density of gas and dust in which the nuclei are embedded. This is a rare and fleeting phase, when the galaxy is neither fully separate nor completely unified, a liminal state that provides a unique laboratory for studying how galaxies transform into new forms through merger. What's even more remarkable is that each of these two nuclei appears to be undergoing its own intense starburst. That's right, ARC-220 doesn't just have one central star-forming region, it has two, and each one is pumping out stars at an extraordinary rate. Observations of the radio continuum and molecular emission lines show that both nuclei are surrounded by dense molecular disks, each no more than a few hundred light-years in diameter, rotating rapidly and forming stars in clusters so compact that they could contain thousands of O-type stars, the most massive, luminous, and short-lived stars in the universe. These twin powerhouses are responsible for much of the galaxy's overall luminosity. And because they're so close together, again, just 1,200 light-years, or about 1/10 the width of the Milky Way, their interactions are constant and intense. Gas flows between them. Shockwaves ripple through the surrounding medium. Gravity stretches, compresses, and reshapes their internal dynamics. The entire system is in flux, teetering on the edge of collapse and fusion. One of the key discoveries that confirmed the presence of two nuclei was the detection of double-peaked emission lines in the spectra of ARP-220. These lines showed that gas was moving at significantly different velocities in two adjacent regions, evidence of two massive objects, each exerting its own gravitational influence. Later imaging in the radio and submillimeter further confirmed the separation, showing two luminous compact sources, each about 300 light-years across, glowing in different parts of the inner galaxy. In many ways, these nuclei are like wounded survivors of a galactic battle, still clinging to their original mass and structure, but forever changed by the collision. They're not serene. They're not stable. They're chaotic zones of high-pressure gas, tangled magnetic fields, rotating dust disks, and waves of new stars. And in their final approach, they're likely dragging along supermassive black holes, each potentially millions of times the mass of our Sun. If both nuclei do, in fact, harbor central black holes, and the circumstantial evidence strongly suggests they do, then ARP-220 is also the site of a future black hole merger. The consequences of such a merger would be cosmic in scale. As the two black holes spiral inward due to gravitational wave emission, they'll eventually collide in a burst of energy that sends ripples through the fabric of spacetime itself. Though this event likely won't happen for millions of years, it places ARP-220 among a rare class of galaxies that could one day contribute to our growing understanding of gravitational waves and black hole evolution. But even before that momentous finale, the nuclei themselves are shaping their environment in profound ways. The immense mass and compactness of these regions create gravitational wells that draw in surrounding gas at high speeds, sometimes resulting in disk-like inflows that further fuel starbursts. The gas here is dense enough to trigger massive star formation, and turbulent enough to produce complex molecular chemistry, including species like CO, HCN, and even more exotic compounds. These chemical fingerprints allow astronomers to map the conditions inside each nucleus, providing detailed snapshots of how stars form in some of the universe's most extreme environments. The proximity of the two nuclei also means that any large-scale feedback, such as a supernova-driven wind or AGN outflow, from one side can affect the other. This cross-contamination of influence is rare in astrophysics, and it's one reason ARP-220 is such an invaluable target for researchers studying the nonlinear effects of galactic feedback. Normally, the energy output from one starburst region might clear gas locally or push it outward, but in ARP-220, that push might interact directly with another starburst region, creating unexpected results and unique turbulence patterns. Interestingly, the two nuclei are not identical. One appears to be more compact and more obscured than the other, while the second shows slightly broader emission lines and possibly hosts stronger outflows. These differences may reflect variations in their original mass, their angular momentum during the merger, or simply the random chaos of the galactic collision. Whatever the reason, they add an additional layer of asymmetry and complexity to an already intricate system. Eventually, the gravitational interaction between the two will cause them to spiral inward, a process that may be partially underway already. As they lose energy through gravitational interactions and dynamical friction with the surrounding medium, they will coalesce into a single core, potentially triggering yet another wave of intense star formation and black hole activity. That final act will be the true birth of a new galaxy, likely an elliptical, and the last echo of the ancient spiral structures that began this cosmic drama. In many ways, these two nuclei are the heartbeats of ARP-220. They pulse with energy, they radiate with intensity, and they represent the last clear memory of what once were two galaxies traveling alone through the cosmos. Now, entwined in an irreversible embrace, they will forge a new future, together. The story of ARP-220 grows even more intense when we focus on what's happening inside each of its twin nuclei. These aren't just passive relics of the original galaxies. They are both undergoing their own nuclear starbursts, which is to say, each is hosting an independently raging furnace of stellar birth within a few hundred light-years of their centers. And remarkably, these starbursts aren't synchronized or symmetrical. They are distinct, chaotic, overlapping waves of energy, flaring in tandem inside a galaxy already pushed to the limits of gravitational equilibrium. A nuclear starburst refers specifically to intense, concentrated star formation taking place in a galactic nucleus, typically confined to the central few hundred parsecs. In ARP 220, this definition is blown to epic proportions. Each nucleus is densely packed with molecular gas, and each harbors a self-contained storm of activity so violent and bright that either one, on its own, would already qualify ARP 220 as a luminous infrared galaxy. Together, they amplify the galaxy's total energy output to ULIRG status, a cosmic double engine, both of its cores firing simultaneously. Observations with high-resolution radio and sub-millimeter arrays like ALMA and the VLA have revealed that each nucleus contains a rotating disk of molecular gas, rich in CO, HCN, and other tracer molecules. These disks are thick, turbulent, and rotating rapidly, with velocities exceeding hundreds of kilometers per second. Within them, gas densities are so high, reaching values of over 10 to 10 particles per cubic centimeter, that they meet the threshold for gravitational collapse almost instantly. Wherever the gas becomes slightly denser, it collapses into stars, sometimes entire clusters of massive stars all at once. Inside each nucleus, the star formation rate is estimated to be dozens of solar masses per year, compressed into regions only a few hundred light-years across. By comparison, our entire Milky Way forms about 1 to 2 solar masses per year spread across 100,000 light-years. Our 220's nuclear starbursts are doing thousands of times more work in less than 1% of the volume. And this isn't gentle star formation. These are bursts under fire, under crushing gravity, intense radiation pressure, and the fury of countless feedback mechanisms. The stars forming in these nuclear bursts are, on average, more massive than those found in normal star-forming regions. It's likely that the initial mass function, IMF, is skewed toward heavier stars, which means more supernovae, more radiation, and shorter stellar lifespans. The whole cycle, formation, life, and explosive death, is accelerated, creating a constant churn of mass and energy in the core. These bursts are visible not in the optical, of course, again, they're hidden by thick dust, but in the radio, infrared, and even X-ray parts of the spectrum. The regions glow in thermal infrared from heated dust, emit strongly in millimeter-wave molecular transitions from dense gas, and flash in radio from supernova remnants and synchrotron emission. Some studies suggest that dozens of supernovae occur per year in the nuclei, far beyond anything ever observed in more quiescent galaxies. It's a literal supernova storm, ongoing, overlapping, and relentless. What makes these nuclear starbursts so extraordinary is how localized yet intense they are. In galaxies like M82, starbursts can cover larger areas. But in ARP 220, the intensity is packed into tight, dense volumes, less than 500 light-years across in each nucleus. This results in energy densities so high that the infrared luminosity per unit volume surpasses most known starburst systems. Each nucleus alone contributes up to 10 superscript 1 solar luminosities, figures that would make them luminous infrared galaxies by themselves. The starbursts also have profound structural effects. They alter the dynamics of the gas, drive powerful outflows of molecular and atomic material, and help stir the turbulent disk environments in which they're embedded. The energy output from newly formed massive stars, through radiation pressure, stellar winds, and eventual supernovae, pushes against infalling gas and against surrounding molecular clouds, creating shockwaves and cavities in the interstellar medium. These feedback processes not only limit the extent of the starburst, but also trigger secondary bursts in surrounding areas as compressed gas collapses anew. Each nucleus seems to have its own unique morphology and feedback behavior. The western nucleus, for instance, is often described as more compact and more obscured, potentially containing a higher surface density of gas and stars. It might even harbor a deeply embedded active galactic nucleus, although this remains a subject of debate due to the extreme dust obscuration. The eastern nucleus appears slightly more extended and might be more dynamically disturbed, possibly experiencing more violent feedback or being at a different stage of its own collapse and starburst life cycle. Interestingly, these nuclear starbursts are not isolated from each other. The distance of 1,200 light-years between them is small on galactic scales, meaning that their gravitational and energetic effects overlap. Material may flow from one to the other. Feedback in one region may compress gas in the other. It's a kind of interacting double starburst, creating complex turbulence and filamentary structures between the nuclei, zones of highly unstable gas that may serve as new sites of star formation or as bridges funneling gas into the centers. These overlapping, simultaneous nuclear bursts are also a rare glimpse into galaxy evolution in fast forward. They show us what might have been happening in galaxies billions of years ago, when mergers were more common and gas was more plentiful. ARP 220, then, becomes more than just a curiosity. It becomes a template for understanding how massive galaxies grew during the cosmic high noon, that epoch when star formation in the universe reached its peak. But the most fascinating part is that this dual-core starburst will eventually resolve. The two nuclei will merge. Their disks will likely collide and compress further, possibly creating one final, even more intense starburst as the last gas clouds collapse under the combined weight of the full system. And eventually, as the fuel runs out or is ejected by powerful winds, the galaxy will settle down. The chaotic starbursts will end. The twin cores will fuse into one. And ARP 220 will begin the slow, quiet life of a massive elliptical galaxy, its days of fire and fury behind it. But for now, the nuclear starbursts burn on, defying entropy and equilibrium, each a cosmic engine pumping out light, heat, and the seeds of a billion future stars. To say that ARP 220 is a galaxy of extremes is not an exaggeration, it's an understatement. Nowhere is this more evident than in the astonishing reality that its central region hosts over 200 compact radio sources, believed to be supernova remnants, all packed within just a few hundred light-years of its dusty core. This makes ARP 220 the most prolific known supernova factory in the nearby universe. In terms of both concentration and number, there's simply nothing else like it within reach of our most powerful instruments. These compact radio sources, detected using the exquisite sensitivity and resolution of radio interferometers like the Very Large Array, VLA, and European VLBI network, EVN, are thought to be individual explosions, or remnants of explosions, from massive stars that lived fast and died young. These stars, likely 8 to 100 times the mass of the Sun, formed in the nuclear starbursts, and then detonated in a blaze of energy only a few million years after their birth. What's left behind? Shock waves, magnetized gas, and sometimes neutron stars or black holes, glows brightly in the radio spectrum as the expanding shells of plasma interact with the surrounding interstellar medium. The radio images of ARP 220's core show a remarkable sight, dozens upon dozens of tiny, bright dots scattered within a tight area, each one marking the aftermath of a cosmic detonation. These supernova remnants, SNRs, are measured to be only a few light-years across, yet they shine steadily in radio wavelengths due to synchrotron radiation, the emission from high-energy electrons spiraling around magnetic fields. It's through this signature that astronomers can identify them even though the surrounding dust makes optical, or X-ray confirmation nearly impossible. The fact that we can see so many supernova remnants in ARP 220's core implies that supernovae are happening there at an incredible rate, estimated at one every year, possibly more. For comparison, in the Milky Way, a supernova occurs once every 30 to 50 years. In ARP 220, the death of massive stars is almost a monthly occurrence. And unlike in the Milky Way, where these events are scattered across a broad disk, ARP 220 supernovae are all erupting in a tightly confined nuclear zone, like firecrackers going off in a pressure cooker. What does such a high rate of supernovae mean for the galaxy? For starters, it means that the interstellar medium, ISM, in the core is constantly being stirred, shocked, and enriched. Each supernova releases energy equivalent to about 10 to the power of 44 joules, enough to blow apart gas clouds, compress others, and distribute heavy elements across the region. These explosions don't just destroy. They also trigger new rounds of star formation by compressing nearby gas and dust, setting off gravitational collapse in adjacent clouds. This creates a kind of chain reaction, a runaway feedback loop where star birth and star death fuel each other in a self-sustaining blaze. The supernovae also shape the structure of the nuclear region. They carve out bubbles and cavities in the dense gas. They drive turbulence, increasing velocity dispersion. They may even contribute to large-scale outflows, winds of gas that escape the core, enriching the outer galaxy or even the intergalactic medium. Some of this material, accelerated by overlapping shockwaves, might leave the galaxy entirely, becoming part of the diffuse cosmic web that threads between galaxies. And then there's the role supernovae play in chemical evolution. These explosions are the primary sites of nucleosynthesis for many of the elements we consider essential for life: carbon, oxygen, magnesium, silicon, and iron. Every atom of calcium in your bones, every molecule of oxygen in your blood, every grain of metal in a planet's core, all of it was forged in the death throes of massive stars. In ARP 220, that process is happening right now, in vast quantities, in real time. The Supernova Factory is seeding the galaxy with the elements of future planets, future stars, and perhaps one day, life itself. There's something else these radio supernova remnants tell us. The nuclear starburst is young. Supernova remnants only shine brightly in the radio for a limited time, usually a few hundred to a few thousand years. The fact that we can see so many at once means that the starburst began relatively recently on cosmic timescales. It's likely still in its first major phase of rapid star formation and destruction. These observations act like a cosmic stopwatch, helping astronomers date the burst, understand its progression, and estimate how much longer it might continue before exhausting its fuel. Interestingly, not all the compact radio sources are simple remnants. Some may be ongoing supernovae, still in the act of exploding or rapidly expanding. Others may be supernova imposters, extremely luminous outbursts from massive stars not yet gone supernova but approaching the end of their lives. And there's even the possibility that some of the sources are embedded black holes or neutron stars, left behind by the explosions, surrounded by dense accretion disks or interacting with binary companions. This opens a tantalizing window into the post-supernova life of stellar corpses in one of the most crowded environments known. In fact, studying these compact radio sources in detail can help astronomers understand how stars die under different conditions. For instance, in normal galaxies, supernovae explode into relatively low-density surroundings. But in ARP 220, the density of the gas and dust around each star is orders of magnitude higher. This dramatically changes the evolution of the shockwaves, the brightness of the radio emission, and the way the remnants cool. By comparing observations in ARP 220 to more isolated supernovae, we gain unique insights into how environment affects stellar death. Moreover, ARP 220's Supernova Factory might one day become a factory of compact objects, a breeding ground for neutron star and black hole binaries. If these remnants remain gravitationally bound in the dense stellar clusters where they were born, they could eventually spiral into each other and merge, releasing gravitational waves detectable by instruments like LIGO and Virgo. So in a very real sense, ARP 220 may not just be a supernova factory, it might also be a gravitational wave nursery. This sheer concentration of supernova remnants also sets ARP 220 apart as a benchmark system in galaxy evolution. Few galaxies exhibit such extreme behavior so close to Earth, making it an ideal target for case studies. In terms of sheer activity, it's as if someone took the entire Orion arm of the Milky Way, home to our biggest star-forming regions, and compressed it into a volume 1,000 times smaller, then turned the dial to 11. The result is awe-inspiring. ARP 220's core isn't just active, it's erupting, constantly, violently, in a storm of light, heat, and matter. Supernovae are not rare punctuation marks in its story, they are its heartbeat, constant and unrelenting. And in watching them, in tracing the paths of those compact radio beacons, we are not just witnessing stars dying, we are watching the cycle of galactic transformation in one of its most intense and spectacular forms. The sheer concentration of supernova remnants in ARP 220 doesn't just make it impressive, it makes it unprecedented. In fact, no other nearby galaxy exhibits anything close to the same density of supernova remnants packed into such a confined space. While many galaxies, especially starburst galaxies like M82 or NGC 253, are known for rapid star formation and frequent stellar deaths. ARP 220 sets the record by a wide margin. It's not just a supernova factory, it's an assembly line of destruction, churning out dying stars faster and more tightly packed than any galaxy we've been able to observe up close. To understand just how extraordinary this is, it helps to do a bit of comparison. The Milky Way, for instance, is estimated to have between 200 and 300 supernova remnants across its entire disk, which spans over 100,000 light-years. ARP 220 has over 200 that we can see within just the central few hundred light-years. That's a concentration at least 1,000 times denser than our own galaxy. Even in M82, one of the best-known starburst galaxies and located a mere 12 million light-years away, we observe a few dozen compact supernova remnants in its central region. Impressive, yes, but nowhere near ARP 220's scale. And M82 is relatively dust-poor compared to ARP 220. If ARP 220 were similarly transparent, we might detect even more remnants hiding behind its layers of warm, opaque dust. So the actual number of supernova remnants may be far higher. What we've seen so far might just be the tip of the iceberg. The ability to even detect this many remnants requires incredibly high-resolution instruments. Arrays like the European VLBI network, EVN, and Very Long Baseline Array, VLBA, stitch together signals from multiple radio telescopes across continents to create a virtual telescope the size of the Earth. Only with this kind of resolution can astronomers pick out the tiny, bright sources nestled so close together within the nuclear regions of ARP 220. Each source measures only a few light-years across at most, yet all of them are crowded into a space smaller than the Milky Way's central bulge. This record-breaking density does more than just set ARP 220 apart. It forces us to rethink the limits of how fast stars can form and die, and what kinds of environments can sustain such activity. The central regions of ARP 220 are so compact, so gas-rich, and so turbulent, that it seems they'd push the laws of stellar evolution to their limits. The galaxy is walking the razor's edge of gravitational instability, radiation pressure, and feedback-driven chaos, and it's still forming stars at a rate of around 100 to 200 solar masses per year. Such intense activity brings the galaxy dangerously close to theoretical thresholds. One such limit is the Eddington limit for starbursts, which describes the maximum luminosity that a region can sustain before the radiation pressure from stars begins to blow gas away, effectively choking off further star formation. ARP 220's nuclear regions are brushing against this limit, yet they continue to hold on to their gas and keep the furnace burning. The record-breaking number of supernova remnants also helps refine our understanding of stellar lifespans in extreme environments. Normally, massive stars live a few million years before ending in a supernova. But in a region like ARP 220's core, where the gas is so dense and turbulent, the interactions between stars, feedback from other supernovae, and rapid enrichment from nearby explosions may accelerate or alter stellar evolution. Some stars might lose mass more quickly. Others might form in clusters where interactions shorten their lifespans. ARP 220 is a natural lab for testing these extremes. There's also something deeply profound in how concentrated this destruction is. Supernovae are not evenly spaced. They are clustered, often erupting in groups within the same star-forming region. In ARP 220, this is taken to a staggering level. Imagine a region the size of a small portion of a single galactic arm in the Milky Way, but within that volume, hundreds of massive stars are detonating one after another, overlapping in time, sometimes even overlapping spatially. It's the celestial equivalent of hundreds of fireworks going off at once in a dense fog, each one carving, seeding, and heating the space around it in a vast, tangled web of energy. And again, it's likely we haven't seen them all. The radio sources we detect are the most compact and brightest. Many more supernovae might have exploded but now faded, or never lit up in detectable radio wavelengths due to their environment. Others might be obscured by layers of even denser gas and dust, their emissions absorbed before they can escape. In fact, some theorists suggest that the true number of recent supernovae in ARP 220's core could be well over 1,000, once observational limitations are accounted for. This would make the galaxy not just the most concentrated, but the most productive supernova environment within 500 million light-years. This record-setting activity doesn't go unnoticed in other wavelengths either. The thermal infrared glow from heated dust, the X-ray output from hot gas stirred by shock waves, and the molecular emission lines from enriched clouds all bear the fingerprints of frequent supernovae. These explosions leave chemical scars, injecting oxygen, carbon, and heavy metals into surrounding gas. And they leave physical ones too, expanding shells, dense knots of compressed gas, and diffuse winds stretching out into the galactic halo. Even the structure of ARC 220's central star-forming region seems to reflect the relentless pace of death and rebirth. Observations show that some of the supernova remnants are arranged in linear sequences, suggesting a chain reaction where one explosion triggered another and another, propagating like fire through a dry forest. This kind of structure is rare in less active galaxies but appears more frequently in compact starburst systems, again placing ARC 220 at the very limits of what we know. These patterns and numbers also open the door to galactic archaeology. By studying the ages, sizes, and luminosities of the remnants, astronomers can reconstruct the timeline of the starburst, when it began, how it peaked, and whether it's slowing down. The density of remnants acts as a fossil record, each one a time capsule from a specific moment in the galaxy's recent past. ARC 220's record isn't just one of numbers. It's a record of what happens when gravity, gas, and chaos reach their maximum. It is the universe's reminder that galaxies are not static. They are living, evolving, explosive entities, capable of producing not just stars and light, but unimaginable firestorms of cosmic birth and death. Every supernova in the core of ARC 220 marks the violent end of a massive star, a giant that lived fast, burned furiously, and died young. These aren't slow-burning, sun-like stars that live billions of years before fading into white dwarfs. These are celestial titans, stars with masses exceeding 8, 10, even 100 times that of the Sun, living just a few million years before they reach a tipping point that triggers a spectacular collapse. And in ARC 220, hundreds of these giants are dying in rapid succession, sometimes side by side, sometimes layered over one another in time, contributing to a relentless cycle of explosive death that defines the galaxy's very structure. In most galaxies, the deaths of massive stars are spaced out, occasional punctuation marks in an otherwise stable cosmic narrative. But in ARC 220, these events are commonplace, woven into the fabric of its turbulent core. Why? Because the nuclear starburst regions, dense, gas-rich, and superheated, are ideal breeding grounds for the most massive types of stars. These giants form in great clusters, embedded within the molecular clouds that dominate the nuclei, born under pressure, nurtured by chaos, and destined for an early death. These stars are so massive that they burn through their nuclear fuel at incredible rates. Hydrogen fuses into helium, then into carbon, oxygen, silicon, and iron in a rapid cascade of energy production. But iron cannot be fused to release energy. It's the end of the line. When a massive star's core becomes iron-rich, the outward pressure from fusion collapses, and gravity takes over. In less than a second, the core implodes. The outer layers crash inward, rebound off the collapsed core, and detonate outward in a supernova explosion, a release of energy so powerful that, for a brief moment, a single star can outshine an entire galaxy. In ARC 220, this process is not an occasional event, it's happening all the time. The sheer number of massive stars forming in its nuclear regions guarantees it. These regions are factories of short-lived luminosity, constantly pushing stars towards supernova thresholds. And every death doesn't just end a stellar life, it reshapes the galaxy around it. These supernovae release shockwaves that travel outward through the dense molecular medium, compressing gas, stirring turbulence, and sometimes triggering more star formation. It's a feedback loop. A star is born in dense gas, lives a few million years, explodes, and the resulting shock compresses more gas nearby, starting the process again. This is part of what keeps the starburst in ARC 220 going, a self-reinforcing storm of life and death. But the role of these supernovae doesn't stop at compression. They also disperse. The explosion can blow apart star-forming clouds, halting formation in some areas and creating cavities in others. They can drive powerful winds that escape the nuclear region entirely, transporting enriched material into the outer galaxy or beyond. These winds may not always be visible, especially in a dust-choked galaxy like ARP-220, but molecular line observations suggest that massive outflows of gas are indeed underway, powered in part by these frequent stellar deaths. The energy budget of each explosion is enormous, about 10 to the power of 44 joules. But even more significant is what they leave behind. Supernovae are the main source of heavy elements in the universe. Iron, nickel, cobalt, calcium, silicon, all synthesized in the core of massive stars and scattered across space by these final detonations. In ARP-220, each supernova becomes a chemical enrichment event, seeding the surrounding gas with the building blocks of planets, moons, and even life. This makes the deaths of these giants not just endings, but beginnings. The gas clouds that will give rise to future stars and planets will be richer, more complex, and more capable of supporting rocky bodies and biological chemistry. In the vast cosmic timeline, events like these lay the groundwork for solar systems that may, billions of years later, ask where they came from. Some of the stars that die in ARP-220 may be so massive, perhaps over 30 or 40 solar masses, that their cores collapse directly into black holes, with or without a visible supernova. Others may explode as hypernovae or parinstability supernovae, rare and incredibly powerful types of stellar death that can release 10 times the energy of a typical core collapse explosion. The environment in ARP-220, with its high pressure, extreme gas densities, and rapid star formation, may very well be a breeding ground for these exotic phenomena, meaning that not only are many stars dying, but some are dying in ways rarely seen elsewhere in the nearby universe. The remnants of these deaths, neutron stars and black holes, may accumulate in the dense clusters near the nuclei. Over time, gravitational interactions can bring these objects into binary systems. Two black holes may spiral toward each other, merging in a final burst of gravitational waves. ARP-220, in this sense, is not just creating stars and killing them, it's also laying the groundwork for the next stage of cosmic drama, where compact objects collide and ring spacetime like a bell. And because of the high rate of supernovae, the interstellar environment of ARP-220's core is unlike anywhere else nearby. It's hotter, more ionized, and more chemically enriched than typical galactic environments. The radiation fields are intense. The pressure is extreme. The magnetic fields are tangled and amplified. It's the ideal laboratory to study the effects of clustered supernovae on gas dynamics, star formation efficiency, and long-term galaxy evolution. Perhaps most evocative of all is the idea that every one of those supernova remnants, those radio sources we detect, is a tombstone for a massive star. Each dot of synchrotron glow is the result of a real explosion that happened in the not-too-distant past, a cataclysmic event that shook the local medium and scattered stardust across the void. Taken together, they paint a picture of a galaxy in the most dynamic phase of its life, a galaxy not gently aging, but raging, violently, in the furnace of its own making. The death of giants in ARP-220 is not a tragedy, it's a necessary, even beautiful part of the cycle. These explosions illuminate the story of stellar evolution, of chemical genesis, and of cosmic transformation. And in this galaxy, they are not rare climaxes, but constant echoes, overlapping and ongoing, shaping a core so dense and hot that it blurs the line between creation and destruction. When a massive star dies in a supernova, it doesn't just vanish quietly, it detonates with such force that the surrounding environment is violently reshaped. In ARP-220, this process happens not in isolation, but hundreds of times within a tightly packed core, each explosion sending powerful shockwaves tearing through the dense molecular clouds. These shockwaves are not merely destructive, they are creative agents, igniting new rounds of star formation by compressing gas to the brink of gravitational collapse. The physics of a supernova shockwave is both dramatic and precise. As the star's core collapses and the outer layers rebound outward at thousands of kilometers per second, a blast wave races through the interstellar medium. In a typical galaxy, this wave expands relatively unimpeded for tens or even hundreds of light years. But in the crushed, gas-rich heart of ARP-220, These waves slam almost immediately into thick, cold molecular clouds, some of which are already on the edge of collapse. The sudden rise in pressure from the shock wave can instantly compress a marginally stable cloud, triggering the gravitational implosion that births a new generation of stars. This creates a feedback loop of cosmic proportions. Massive stars form, live short, brilliant lives, then die in supernovae, whose shockwaves in turn compress more gas, forming more massive stars, which then die and restart the cycle. In most galaxies, this cycle is moderated, spread out over large volumes. In ARP 220, however, it is intensely localized, squeezed into a few hundred light-years where each supernova's influence extends across multiple stellar nurseries. The result is a chain reaction of star formation, faster, more intense, and more chaotic than anywhere else nearby. The energy carried by these shockwaves is immense. A single supernova releases about 10 to the power of 44 joules, enough to power all of Earth's energy consumption for trillions of years. In ARP 220's core, where supernovae may occur once per year or more, this means a constant injection of energy into the surrounding medium. These shockwaves not only compress gas but also stir it, increasing turbulence and altering the internal pressure of gas clouds. This turbulence isn't just random chaos. It becomes part of the star formation recipe, influencing how gas fragments, how many stars form, and what kinds of stars emerge. Interestingly, in ARP 220, the extreme density of gas also alters how these shockwaves behave. In lower density regions, a supernova can expand for thousands of years before slowing. In ARP 220's nuclear starburst, however, the surrounding gas is so dense, reaching values of over 10 particles per cubic centimeter, that the shockwave slows and cools rapidly, depositing its energy much more efficiently. This helps create shells of compressed gas, often visible in molecular line observations, which mark the front lines where shock energy has triggered new star formation. Moreover, many of these supernova shockwaves overlap, creating zones where multiple fronts collide. These intersections are some of the most active, unstable environments in the galaxy. There, gas can reach pressures millions of times higher than in the Milky Way's disk, resulting in the rapid formation of extremely dense, massive star clusters. Clusters so packed with stars they rival the density of globular clusters, but are much younger. These clusters themselves become new centers of radiation and feedback, emitting UV light, stellar winds, and, eventually, more supernovae. In this way, shockwaves in ARP 220 don't just initiate star formation, they help sculpt it. They determine the geometry of new star-forming regions, the spacing of clusters, and even influence the initial mass function, which decides what kinds of stars are most likely to form. In the extreme environment of ARP 220, that IMF appears skewed toward massive stars, possibly due to the high-pressure conditions generated by overlapping shockwaves and rapid cooling of compressed gas. The cumulative effect of all this activity is nothing short of transformative. As shockwaves spread outward, they begin to create larger-scale structures, cavities, shells, and bubbles that can be observed in radio and submillimeter wavelengths. Some of these features are tens or hundreds of light-years across and are filled with hot, ionized gas, expanding slowly as the combined pressure of radiation, thermal energy, and momentum pushes against the surrounding medium. These structures act like breathing lungs for the galaxy, periodically inflating and deflating as waves of energy pass through them. In addition to fostering new star formation, the energy from shockwaves also heats the interstellar medium, especially the diffuse molecular gas between denser star-forming regions. This heating alters the chemistry of the gas. Molecules that can survive in cold, dark clouds begin to break apart, while new, exotic molecules form in the energetic soup left behind. Observations of ARP 220 have revealed an abundance of complex molecules, such as HCN, HCO+, and even CH3OH, methanol, all of which suggest that the shock-driven chemistry in its core is extraordinarily rich. These shock-induced chemical reactions don't just affect the gas. They may also help form prebiotic molecules, organic compounds that are considered precursors to life. In a galaxy like ARP 220, these molecules are unlikely to survive long, given the harsh conditions. But the fact that they can form at all, in such extreme environments, tells us something powerful about the resilience of life's building blocks in the universe. The energy from supernova shockwaves also has one final, far-reaching effect: the creation of large-scale galactic outflows. In the nuclear regions, the constant churning from star formation and stellar death builds pressure that eventually forces gas outward. When shockwaves converge or when enough energy is deposited in one region, material can be launched vertically out of the galactic plane. Observations suggest that ARP-220 is already producing multiphase outflows, with both warm ionized gas and cold molecular material being ejected into its halo. These outflows are crucial. They regulate the starburst, preventing it from burning through its gas too quickly. They enrich the galaxy's outskirts with metals and dust. And over time, they contribute to the galaxy's eventual transition from a violent, starbursting merger into a quieter, more stable elliptical galaxy. This evolution is driven, in no small part, by the relentless energy of supernova shockwaves. So while it may seem like the end for the stars that explode in ARP-220, their legacy continues. Their deaths send ripples through space that ignite, reshape, and renew. They are both destroyers and creators, each one a punctuation mark in the ongoing story of cosmic evolution. In ARP-220, these shockwaves are not the rare exception. They are the heartbeat of the galaxy, pulsing energy into every corner of its turbulent core. Near the tumultuous nuclei of ARP-220, nestled within its dense, dusty heart, lie some of the most extreme star clusters ever observed in the nearby universe. These are not casual gatherings of stars. They are compact, gravitationally bound cities of stellar giants, crammed into volumes so small and so active that they rival and, in some cases, exceed the intensity of globular clusters. Formed under crushing pressures and fueled by the chaos of a recent merger, these clusters are the immediate children of the starburst, a testament to what happens when gravity, gas, and time all converge in a cosmic furnace. These young clusters are incredibly dense. Packed into regions just a few light years across, they can contain tens of thousands, even hundreds of thousands of stars. Many of these stars are massive, short-lived blue giants and O-type stars, some more than 50 times the mass of the Sun, all burning hot and fast. These clusters aren't quiet neighborhoods. They're violent, radiant arenas, where stellar winds from newborn stars collide, radiative pressure surges, and supernovae erupt in rapid succession. The gravitational binding energy of these groups is enormous, allowing them to remain intact despite the chaos around them. What makes these clusters even more fascinating is the environment in which they formed. Our 220 central region is a soup of cold molecular gas, intense turbulence, and radiation pressure. This environment doesn't just allow star formation, it forces it. As gas is funneled into the center by the dynamics of the merger, it becomes compressed to such an extent that it fragments into compact, high-mass clumps. Within these clumps, gravity takes over, collapsing them into ultra-dense cores that birth thousands of stars in a single, explosive event. The result? Star clusters that are denser than anything typically found in the Milky Way. Observations using instruments like the Atacama Large Millimeter/Submillimeter Array, ALMA, and the Hubble Space Telescope, in near-infrared bands, have revealed these clusters as bright, point-like sources, often buried beneath veils of dust. In visible light, they remain hidden. But in the infrared and radio, their true nature emerges, brilliant, massive, and newly born. Some are still embedded within their natal clouds, while others are already lighting up their surroundings, creating expanding H2 regions, bubbles of ionized gas that mark the presence of energetic ultraviolet radiation from their hot stellar inhabitants. These clusters are also crucibles of feedback. Their massive stars pour out UV radiation, generating intense stellar winds, streams of charged particles that blow out into the surrounding medium. These winds, combined with pressure from radiation and the inevitable detonation of supernovae, help sculpt the interstellar gas, driving shockwaves that compress nearby clouds and propagate the starburst further. At the same time, they blow cavities in the gas, clearing out pockets within the nuclear region and allowing energy to escape vertically from the plane of the galaxy. Because of the high stellar density, it's not uncommon for stars in these clusters to interact gravitationally, altering orbits, creating binaries, and even colliding in extreme cases. These interactions can accelerate stars to high velocities or cause massive binaries to form and merge, possibly producing black holes or gamma-ray bursts. Some theorists believe that in such environments, we might even find the precursors to intermediate-mass black holes, born from successive mergers of massive stars and stellar remnants at the cluster's core. The chemical composition of these clusters is another fascinating detail. Since they formed in an environment already enriched by supernovae from earlier bursts, their stars likely contain higher than average metallicities, meaning they're richer in elements heavier than helium. This makes them chemically distinct from many globular clusters, which formed early in the universe's history with very low metallicity. In contrast, ARP-220's clusters are metal-rich, high-pressure populations, more similar to those we expect to find in merging galaxies or the dense cores of ultraluminous starbursts at high redshift. Their youth is also a factor. Many of these clusters are less than 10 million years old, placing them among the youngest stellar systems observable in detail. Their brightness, heat, and stellar composition make them ideal laboratories for studying early cluster evolution, massive star life cycles, and the initial mass function, IMF, under extreme conditions. The IMF in these clusters may be skewed toward higher mass stars, meaning that more giants are born than would be expected in more quiescent environments. If true, this alters the expected rate of feedback, chemical enrichment, and black hole formation for the entire galaxy. What's even more compelling is that some of these clusters may not survive indefinitely as individual units. Over millions of years, as they drift through the dense core of ARP-220, gravitational interactions with other clusters, gas clouds, and the tidal forces of the central mass concentrations may disrupt them. Some will dissolve into the broader stellar field of the merged galaxy, contributing to its dense central bulge. Others might sink toward the very center, potentially feeding the growth of the central black holes or forming nuclear star clusters, tightly bound stellar systems surrounding galactic cores. But some will survive. And the ones that do may become protoglobular clusters, eventually evolving into the kinds of ancient, spherical star systems we see today around the Milky Way and other galaxies. If so, ARP-220 is giving us a direct glimpse into how globular clusters might have formed in the early universe, not in peaceful isolation, but in the aftermath of titanic galactic collisions, in regions of intense pressure, heat, and dust, where thousands of massive stars ignited nearly all at once. It's also likely that many of the compact radio sources observed in the core of ARP-220, believed to be supernova remnants, are directly associated with these star clusters. That makes sense. If you have tens of thousands of massive stars in a few parsecs, you're going to have a correspondingly high rate of death. Each cluster becomes not only a birthplace of stars but a repository of remnants, littered with neutron stars, black holes, and the expanding shells of former giants. In the broader view of galactic evolution, these compact star clusters play a key role in redistributing mass and momentum within the galaxy. Their gravitational fields influence local gas dynamics. Their feedback shapes star formation efficiency. And as they evolve, merge, or are disrupted, they help define the long-term stellar architecture of the merged system that will eventually become a quiescent elliptical galaxy. ARP-220, in essence, is a stellar metropolis in its most explosive phase. And its compact star clusters are the neighborhoods where this drama is playing out in the highest resolution. Each cluster is a microcosm, a miniature galaxy, brimming with heat, light, force, and change. And each one is helping to write the next chapter of ARP-220's story. If there's a single ingredient that fuels the furious transformation of ARP-220, it's molecular gas, cold, dense, and everywhere. This galaxy, particularly in its central kiloparsec, is a reservoir of molecular mayhem, a churning, pressure-cooked region where vast clouds of gas are constantly being stirred, crushed, heated, and collapsed into stars. And not just a little gas. ARP-220 contains one of the highest concentrations of molecular gas known in any galaxy in the local universe. This central core is not a quiet well of star-forming potential. It's a boiling cauldron of chemistry and chaos, where the interstellar medium has been pushed to extremes few galaxies ever reach. At the heart of this chaos is carbon monoxide, CO, one of the most abundant and easily detectable molecules in interstellar space. Because molecular hydrogen, H2, the actual primary ingredient of star formation, is nearly invisible to telescopes due to its lack of a strong dipole moment, astronomers often rely on CO as a tracer. In URP 220, CO is found in such staggering quantities that it lights up millimeter and sub-millimeter telescopes like ALMA and NOMA with intense emission lines, mapping out where the densest gas lies. Estimates suggest that URP 220 harbors over 10 billion solar masses of molecular gas, concentrated in the inner few hundred parsecs, an almost incomprehensible amount packed into such a small volume. For comparison, the Milky Way contains around 1 to 2 billion solar masses of molecular gas spread across its entire disk. In URP 220, this material has been compressed by the violent gravitational torques of the merger, funneled inward by tidal forces, and piled into a thick, turbulent disk in the central region. This gas doesn't just sit there quietly. It's in a perpetual state of upheaval, colliding, fragmenting, and interacting with feedback from supernovae and stellar winds. Its temperature, surprisingly, isn't always low. Regions of the gas can reach temperatures well above 100 K, far hotter than typical star-forming clouds. And yet, despite this heat, the pressures in URP 220's core are so high that molecules remain bound, and collapse can still occur, leading to runaway star formation in some zones and temporary quenching in others. What's more, this gas is chemically rich. Surveys with ALMA have revealed a menagerie of molecules in URP 220, including HCN, HCO, CN, CH3OH, methanol, and even complex organic molecules that hint at prebiotic chemistry. The presence of these molecules tells us that the galaxy's core is not just hot and dense, but also chemically evolved, enriched by repeated cycles of stellar birth and death. Some molecules, like HCN, hydrogen cyanide, are known tracers of dense gas, with critical densities 100 to 1000 times higher than CO, and in URP 220, HCN is found in extreme abundance, suggesting a vast inventory of gas already poised to form stars. This abundance creates something of a paradox. With such an intense supply of fuel and such ferocious star formation, why hasn't URP 220 already burned through all its gas? Part of the answer lies in the self-regulating nature of feedback. While star formation is underway, the radiation, winds, and supernovae from massive stars constantly inject momentum and energy into the surrounding clouds, stirring them, breaking them apart, and sometimes halting collapse altogether. This feedback maintains a delicate balance, enough disruption to prevent the gas from collapsing too quickly, but not enough to expel it outright. For now, that balance holds. But it won't forever. The structure of the molecular gas in URP 220 is also unique. High-resolution observations show that the central kiloparsec contains two compact gas disks, each surrounding one of the galaxy's twin nuclei. These disks are rotating rapidly, with turbulent line widths of 300 to 500 km/s, indicating that the gas is not just orbiting quietly but is under intense gravitational and kinetic stress. Collisions between these rotating flows may be contributing to the ongoing starbursts by triggering cloud collapse on short timescales. Some models suggest that the molecular gas in URP 220 is arranged into a thick, warped disk, with gas streams connecting the two nuclear regions. The overlapping shock fronts, shear forces, and tidal distortions in these regions mean that no part of the gas disk is stable for long. Every cloud is either forming stars, being shredded by turbulence, or being reshaped by feedback, often all at once. Interestingly, some of the most intense molecular line emissions in URP 220 come from very high excitation transitions, which typically require intense radiation fields, mechanical heating from shocks, or both. This suggests that much of the gas in URP 220 isn't in cold, quiescent clouds, but rather in shock-heated filaments and turbulent eddies, constantly interacting with supernova remnants and stellar winds. It's not the calm conditions that one might associate with peaceful star formation, but rather violent, pressured environments, where gas is squeezed into stars as if by force. And in these conditions, time is compressed. In the Milky Way, a typical molecular cloud may last tens of millions of years before forming stars. In ARP 220, clouds may collapse and form entire clusters in just a few million years, only to be destroyed by feedback and reshaped into new clouds shortly afterward. The molecular gas, therefore, is not static. It's part of an evolving cycle, where gas is constantly converted, disrupted, recycled, and enriched. One of the most compelling aspects of ARP 220's molecular chaos is that it provides a template for understanding high-redshift galaxies. Galaxies in the early universe were often rich in molecular gas, turbulent, and undergoing frequent mergers, much like ARP 220 today. By studying this galaxy in exquisite detail, we get a window into the past, seeing what primordial starbursts might have looked like, and how the first massive galaxies assembled their stars, black holes, and heavy elements. The chaos in ARP 220's molecular core also sets the stage for its eventual evolution. As gas is gradually consumed by star formation or expelled in winds, the starburst will slow, the radiation field will soften, and the turbulent energy will dissipate. The galaxy will cool and settle, eventually transforming from a luminous infrared monster into a more subdued, quiescent elliptical system. But for now, in this brief cosmic moment, it is a roiling storm of molecular complexity, driven by the legacy of a galactic collision and the raw power of gravitational convergence. So when we look at ARP 220's molecular gas, we're not just seeing star-forming material, we're seeing the engine of its transformation. Every filament, every cloud, every molecule is a piece of the machine, grinding away under immense pressure, building stars, recycling elements, and pushing the galaxy toward its next evolutionary stage. At the heart of ARP 220's storm of chaos, beyond the molecular gas, the bursting stars, and the dying giants, lies a deeper mystery still cloaked in shadow, the potential presence of not one, but two supermassive black holes. These aren't the kind you find serenely anchoring the centers of typical galaxies. These black holes, if they exist, are buried beneath layers of dust and gas so thick that even our most powerful optical telescopes cannot peer through them. To see any hint of them at all, scientists must rely on the longest wavelengths of light, scanning with infrared and radio telescopes to tease out signals that might betray their existence. The suspicion arises from a fundamental understanding of what happens when galaxies merge. Most large galaxies, including spirals like the Milky Way, are known to contain supermassive black holes at their centers. When two such galaxies collide, their black holes don't vanish. Instead, they begin an inevitable gravitational dance, slowly spiraling toward each other over millions of years, pulled together by dynamical friction, their orbits shrinking until they eventually form a binary system, and perhaps one day, merge in a burst of gravitational waves. In ARP 220, the two distinct nuclei, still visible about 1,200 light-years apart, are each embedded within compact, rotating disks of gas and dust. This alone strongly suggests that each nucleus is the surviving core of a once separate galaxy, and if both original galaxies had their own central black holes, as expected, then ARP 220 should now contain two active or dormant black holes, each potentially still accreting material, albeit heavily obscured. Detecting them, however, is not easy. In most galaxies with active black holes, we see telltale signs, powerful X-ray emissions from the hot corona of gas swirling around the black hole, or bright jets and lobes of radio emission launched at near-light speed from the poles of the accretion disk. But in ARP 220, the optical and even X-ray light is blocked by dust so dense that not even high-energy photons can escape unscathed. This leaves only indirect clues, hints in the radio and mid-infrared spectrum, and spectral lines that deviate from those produced by star formation alone. Some of these clues are tantalizing. For example, deep X-ray observations with Chandra and NuStar have detected faint, hard X-ray sources consistent with heavily obscured AGN, active galactic nuclei, particularly in the western nucleus. The X-rays we do detect are of high energy and appear to come from regions no larger than a few parsecs, a size consistent with compact, accreting black holes rather than extended star-forming regions. These observations suggest the presence of a Compton-thick AGN, meaning that even the hardest X-rays are scattered or absorbed by dense gas clouds, making detection exceptionally difficult. In the infrared, subtle features in the mid-infrared spectra taken by Spitzer and ground-based observatories hint at emission lines from hot dust that are more consistent with AGN heating than with starburst activity. Some researchers argue that these signatures, combined with the compactness and luminosity of the nuclei, indicate that both nuclei may host accreting black holes, each enshrouded in cocoons of star-forming gas and dust. And then there's the kinematics, the motion of the gas itself. Observations with ALMA and other radio interferometers reveal complex, high-velocity gas flows in both nuclear regions, including possible rotating disks and outflows with velocities that can't be explained by stellar winds alone. Such gas dynamics are often associated with black holes, whose immense gravity pulls material into tight orbits and occasionally ejects it in powerful jets or winds. In ULIRG 220, the evidence of molecular outflows, particularly near the western nucleus, may indicate the presence of a hidden AGN driving gas outward at several hundred kilometers per second. One particularly intriguing line of research is the idea that both nuclei are in different evolutionary stages. Some models suggest that the western nucleus is further along in feeding its central black hole, potentially making it more active, while the eastern nucleus may be dominated by starburst activity for now. Over time, as the merger progresses, the gas dynamics may change, fueling the eastern nucleus and awakening its black hole as well. Yet the story is still far from certain. Other researchers argue that the extreme starburst activity alone could explain many of the observations that hint at black holes. Starbursts can drive winds, heat dust, and emit X-rays, especially when clustered supernovae and massive stars dominate a region. The central question becomes, how much of ULIRG 220's energy is from stars, and how much is from black holes? It's not an easy balance to determine, especially with such heavy obscuration. But this challenge is precisely what makes ULIRG 220 such a fascinating laboratory. If it does indeed host dual-obscured AGN, it would be one of the closest and best examples of two supermassive black holes in the process of merging. This makes it invaluable not only for understanding the dynamics of galaxy evolution, but also for exploring the early stages of black hole binary formation, a key puzzle in gravitational wave astronomy. Looking forward, the James Webb Space Telescope may provide sharper answers. With its powerful mid-infrared instruments, JWST is capable of peering deeper into the dusty heart of ULIRG 220 than any telescope before it. By resolving fine structures in the warm dust, it may uncover definitive spectral features, such as the high excitation lines of neon and oxygen, that are unmistakable signs of AGN activity. It may also help distinguish the heating effects of AGN from those of young stars, helping us refine the models that attempt to separate their contributions. Additionally, future very long baseline interferometry, VLBI, in radio wavelengths may resolve fine-scale structures, compact, high-brightness regions that can only be produced by AGN cores or jets. If such features are found in one or both nuclei, the case for obscured black holes becomes significantly stronger. Until then, ULIRG 220 remains a case of buried giants, possibly hiding in plain sight. If the black holes are there, and all evidence suggests they are, then they are currently shrouded, dormant or simmering, waiting for the chaos around them to align in just the right way to ignite them into fully active quasars. Or perhaps, they already are active, whispering instead of shouting, their voices muffled beneath the weight of billions of solar masses of gas and dust. And one day, if the dance continues and the merger completes, these two black holes will spiral inward, drawn together by gravity and the dynamical friction of surrounding stars. They will eventually collide, forming a single, larger black hole in an event so cataclysmic it will ripple across space-time, sending gravitational waves echoing across the cosmos, waves we may one day detect. But for now we wait. We listen. And we peer through the dust with the finest instruments we have, searching for the subtle footprints of what may be two of the most fascinating and hidden monsters in our cosmic neighborhood. If ULIRG 220 does indeed harbor two supermassive black holes, one in each of its still distinct nuclei, then it stands as more than just a beacon of chaos and star formation. It becomes a ticking clock, counting down toward one of the most spectacular events in astrophysics, the merger of two cosmic titans. These aren't stellar mass black holes formed in supernovae. They're millions, perhaps even hundreds of millions, of solar masses each, dark, gravitational engines that anchor entire galaxies. And their eventual collision would not only reshape the core of ARP 220, but send ripples through the very fabric of spacetime, in the form of gravitational waves. When galaxies merge, their central black holes begin an extended, intricate dance. At first, the two black holes drift within the gravitational potential of the newly forming galaxy. The chaotic gravitational landscape of ARP 220's core, with its dense star fields, molecular clouds, and tidal torques, acts as a kind of cosmic brake, gradually removing the orbital energy of the black holes. This phase, known as dynamical friction, is relatively slow, taking tens to hundreds of millions of years. Stars that pass near each black hole steal a bit of its energy, flung into wider orbits or ejected entirely from the galactic center, while the black holes are slowly drawn inward. As they close the distance, falling from a few kiloparsecs to mere parsecs, their mutual gravity begins to dominate. They form what's known as a bound binary, orbiting each other like dancers locked in a gravitational waltz. If ARP 220's black holes are at this stage, they are likely separated by just a few light years, encased in an environment so dense and obscure that even high-resolution radio observations struggle to distinguish them. This binary system doesn't remain static. It interacts with the surrounding environment, stars, gas, and dark matter, all of which work to extract angular momentum and shrink the orbit. In gas-rich environments like ARP 220, this process can be particularly efficient. The binary carves out a central cavity in the gas disk, creating spirals and wakes that channel gas inward, not just feeding the black holes, but dragging them ever closer together. Eventually, the separation shrinks to milliparsecs, and at this stage, gravitational radiation, the final mechanism of energy loss, begins to dominate. The orbit decays rapidly. The black holes spiral in faster and faster, their orbital velocities increasing until they are hurtling around each other at a significant fraction of the speed of light. The final moments of this dance are brief but unimaginably intense. The curvature of spacetime itself becomes dynamic, warping outward in gravitational waves that carry away the last remnants of energy before the two singularities finally plunge into one another, fusing into a single, larger black hole. This final merger would release an immense burst of gravitational radiation, equivalent in energy to several solar masses converted entirely into gravitational waves. For a brief moment, it would be the most energetic event in the universe, not in light or matter, but in the undulating geometry of spacetime itself. These waves would ripple outward at the speed of light, expanding in all directions. Eventually, some of them would pass through our solar system. Space itself would stretch and contract by the tiniest amounts. Distances between atoms would shift ever so slightly, too small for the human eye to detect, but not too small for our most sensitive instruments. At present, LIGO and Virgo, our current gravitational wave observatories, are sensitive to black hole mergers involving stellar mass black holes, tens of times the mass of the Sun. But the merger in ARP 220 would involve supermassive black holes, which produce waves at much lower frequencies, far below what LIGO can detect. For those signals, we look to the future, specifically to LISA, Laser Interferometer Space Antenna, a planned space-based gravitational wave observatory set to launch in the 2030s. LISA will consist of 3 spacecraft forming a triangle millions of kilometers across, floating in solar orbit. This massive detector will be able to hear the slow, deep hum of supermassive black holes as they spiral toward their destiny. If ARP 220's black holes merge within the next few 100 million years, LISA may be the one to listen in on the final symphony, detecting the subtle crescendo as the black holes spiral inward, merge, and then ring down like a cosmic bell. But the significance of this event isn't just observational, it's transformational. A black hole merger at the center of a galaxy fundamentally alters the surrounding environment. The newly formed black hole, often recoiling slightly from the asymmetric emission of gravitational waves, may shift its position, dragging some gas and stars with it. This recoil, called a gravitational wave kick, can in some cases be strong enough to eject a black hole from the center of its galaxy entirely. In ARC 220, such a kick is likely to be modest, thanks to the chaotic, nearly symmetric environment, but it could still displace the black hole for thousands of years. Moreover, the merger injects enormous energy into the surrounding medium, not directly through light, but through the gravitational reshaping of the central region. Gas flows may be disrupted, star formation quenched or triggered anew, and the structure of the inner galaxy transformed. Some simulations even suggest that black hole mergers can drive the final stages of galactic evolution, signaling the end of the starburst phase and the beginning of a more passive, quiescent era. There's also the question of timing. Are we catching up 220 in the middle of this process? Has the binary already formed? Is it still spiraling inward, or is the merger millions of years away? We don't yet have a complete answer. But signs of disturbance in the gas, the peculiar emission lines, the compact radio sources, and the buried X-ray signatures all suggest we may be seeing the precursors to this event, a rare glimpse into a cosmic process that bridges the birth and death of galaxies. And ARC 220 wouldn't be alone. As we look farther into the universe, we find more merging galaxies, many of which likely host similar dual black hole systems. ARC 220 just happens to be close enough to study in exquisite detail, a training ground for learning how to recognize and interpret the signatures of black hole mergers across cosmic history. The eventual coalescence of the black holes in ARC 220 will be both an ending and a beginning. An ending to the chaotic merger that began hundreds of millions of years ago, when two spiral galaxies collided, and a beginning for a new phase of galactic life, a massive elliptical galaxy, formed in fire and force, now anchored by a single, monstrous black hole at its heart. Until then, the dance continues. Hidden beneath the veils of dust, surrounded by storms of gas and waves of radiation, the black holes of ARC 220 spiral inward. Slowly. Inevitably. Waiting for the moment when they become one, and the universe listens. The gravitational ripples from a supermassive black hole merger, like the one expected in ARC 220, are not just spectacular in their magnitude, they are profoundly informative. If we are fortunate enough, someday in the not-too-distant future, to detect such waves from this galaxy or one like it, we will not only witness the echo of a cosmic collision, but we will also gain a window into some of the deepest and most pivotal processes of galactic evolution. Gravitational waves are fundamentally different from light. Light can be absorbed, scattered, or blocked by intervening matter, especially in systems like ARC 220. Where thick layers of gas and dust obscure much of the visible and even high-energy spectrum. Gravitational waves, on the other hand, pass through matter virtually unimpeded, traveling across the cosmos unaltered by the medium they traverse. This means that when we detect them, we are catching a pure signal, an uncorrupted whisper from the heart of a cataclysm. And what a whisper it would be! The merger of two supermassive black holes, such as those suspected in ARC 220, would create gravitational waves at low frequencies, in the range of millihertz, far too slow for current ground-based detectors like LIGO and Virgo to catch, but ideal for space-based observatories like the upcoming LISA mission. Once operational, LISA will be able to detect the in-spiral, merger, and ring down of black hole binaries with masses from 100,000 to over 1 billion suns, and it may be the first to detect such an event from a galaxy like ARC 220. If detected, these waves would offer a treasure trove of information. The frequency and amplitude of the gravitational wave signal would immediately reveal the masses of the merging black holes. Their spin, a fundamental property that governs how black holes warp space and time, can also be measured based on how the wave's frequency evolves just before the merger. If the black holes are spinning in the same direction as their orbit, the merger happens differently than if their spins are misaligned or retrograde. This kind of information is impossible to obtain from electromagnetic observations alone. Beyond measuring the properties of individual black holes, such a detection would shed light on the environment and history of the host galaxy. For instance, the alignment of spins and the orbital eccentricity can hint at how the black hole binary formed. Was it a smooth merger in a gas-rich environment, like ARC 220? Where dynamical friction and gas drag brought the black holes together in an orderly fashion? Or was it a chaotic, gas-poor encounter in which stars and gravitational kicks played the dominant role? Each scenario leaves an imprint on the gravitational wave signal. But perhaps even more important is what this means for our understanding of galaxy evolution as a whole. Supermassive black holes and their host galaxies appear to be intimately connected. The M-sigma relation, which links the mass of a galaxy's central black hole to the velocity dispersion of its stars, suggests that galaxies and black holes grow together. Yet the mechanisms behind this coevolution are still murky. Are black holes shaping their galaxies through feedback? Or are galaxies shaping their black holes through gas supply and mergers? Gravitational waves offer a new way to probe this relationship. By measuring the rate of black hole mergers across cosmic time, we can reconstruct how frequently galaxies collide and how often their central black holes grow by merging. If we detect ripples from ARP 220's future merger, we'd be catching one link in that vast cosmic chain, direct evidence of black hole growth via galactic interaction. Accumulate enough of these detections, and we begin to map the population history of black holes themselves, revealing how the universe built the gravitational monsters we see today. Moreover, if we can identify the host galaxy of a gravitational wave event, say, by correlating the direction of the wave with optical or infrared surveys, we gain even more power. We can examine the stellar populations, gas content, metallicity, and morphology of the host galaxy to see how black hole mergers affect their surroundings. Did star formation cease after the merger? Did the galactic center become more quiescent, or was it re-energized by the event? In a case like ARP 220, this information could help us understand how mergers transition galaxies from blue, star-forming spirals to red, dead ellipticals. And let's not forget about the aftermath. A black hole merger releases more than just gravitational waves. Depending on the precise conditions of the merger, especially asymmetries in mass and spin, the resulting black hole may receive a gravitational recoil, essentially a kick from the anisotropic emission of waves. In some extreme cases, this kick could reach thousands of kilometers per second, enough to eject the black hole from its galaxy entirely. In ARP 220, where the gravitational potential is deep and the merger likely symmetric, such a recoil may be smaller. But even a few hundred kilometers per second could displace the new black hole from the galactic center, temporarily or permanently. Observing such a displacement in concert with a gravitational wave signal would provide smoking gun evidence of a recent black hole merger. The gravitational wave signal also carries information about the ringdown, the final stage after the black holes have merged and the new black hole settles into a stable configuration. This stage is governed by the quasi-normal modes of the black hole, essentially, how space-time rings after being struck like a bell. These modes are predicted precisely by general relativity, and detecting them allows us to test Einstein's theory in the most extreme conditions imaginable. Any deviation from the expected signal could point to new physics, such as modified gravity or the presence of exotic fields. In this sense, the merger of the black holes in ARP 220, if and when it happens, would be not just a spectacular celestial event, but a cosmic experiment. It would let us test our theories of gravity, black hole dynamics, galaxy evolution, and cosmology, all in one fell swoop. And if we can detect the precursor in spiral, LISA could observe the system for years before the final merger, allowing us to refine the expected signal and coordinate with electromagnetic telescopes to catch any accompanying radiation, perhaps from the surrounding accretion disk being disturbed or from gas shocked by the merger. This kind of multi-messenger astronomy, combining gravitational waves with light across the spectrum, is the future of astrophysics. And ARP 220, with its dense dust, furious starbursts, and probable twin black holes, stands as one of the most promising nearby laboratories to prepare for that future. For now, the gravitational ripples of ARP 220's fate remain theoretical. But with every advancement in technology, with every new mission like JWST, LISA, and next-generation radio arrays, we inch closer to catching those waves, to listening, at last, to the deep, rhythmic heartbeat of colliding galaxies. While the core of ARP 220 remains shrouded in an almost impenetrable fog of dust and molecular gas, rendering it all but invisible to optical telescopes. It is radio astronomy that has pierced this veil. It is thanks to radio telescopes, both single-dish and interferometric arrays, that we've uncovered many of the most jaw-dropping insights into this galactic furnace. In a place where stars explode by the hundreds, black holes possibly lurk unseen, and molecular clouds churn in violent rotation, radio waves carry the clearest signals, unaffected by the dense, obscuring medium that blocks so much else. Unlike visible light, which is scattered or absorbed by dust, radio waves sail through unimpeded, allowing us to directly observe the hidden mechanics of ARP 220's interior. What might appear as a bland smudge in an optical image is revealed in intricate, dynamic detail in the radio spectrum. The very structure of the double nuclei, for example, each just 1,200 light-years apart, was resolved and mapped using radio interferometry. This is no minor feat. To distinguish between such closely packed, heavily obscured regions at a distance of 250 million light-years requires extraordinary resolution, only possible with the technique of very long baseline interferometry, VLBI. VLBI connects radio telescopes across continents, synthesizing an Earth-sized telescope that can resolve features as small as a few light-years across in distant galaxies. It was through this method that scientists first discovered the over 200 compact radio sources nestled in the core of ARP 220, most of them interpreted as supernova remnants, their radio emission glowing from the shock-heated electrons spiraling in magnetic fields. This alone was a landmark moment. Never before had astronomers seen such a concentrated cluster of supernovae, suggesting an unparalleled rate of stellar death and birth in a single galactic core. But these observations didn't just count explosions. They painted a picture of timing and evolution. By tracking how the brightness of individual radio sources changes over time, astronomers can differentiate between young supernovae, older remnants, and possibly active galactic nuclei, AGNs. Some of these sources rise and fade in brightness, indicating recent detonations of massive stars, while others remain constant, likely long-dead remnants still glowing in the aftermath. Radio telescopes also provide a census of the gas. Carbon monoxide, CO, and other molecules emit strongly in the millimeter and submillimeter wavelengths, revealing where the molecular clouds are concentrated, how they move, and what temperatures and densities they maintain. Instruments like the Atacama Large Millimeter/Submillimeter Array, ALMA, have been instrumental in mapping the distribution of molecular gas within ARP 220's central kiloparsec. With ALMA's exquisite resolution, scientists have tracked rotating disks of gas around both nuclei, high-velocity outflows, and even filamentary structures possibly feeding star formation or accretion processes. Moreover, radio recombination lines, tracers of ionized hydrogen, allow us to estimate the amount and spread of ionized gas, giving insights into stellar populations, starburst regions, and areas impacted by feedback from young, hot stars. This is particularly useful in starburst galaxies, where ionized gas often follows the pressure waves of recent supernovae, helping researchers reconstruct the history and cadence of star-forming episodes. Another powerful diagnostic tool in the radio is maser emission, the cosmic equivalent of lasers, but in the microwave range. In extreme environments like ARP 220's core, water, hydroxyl, OH, and methanol molecules can produce intense maser emission, often amplified by dense clouds and strong radiation fields. ARP 220 is known for its powerful OH megamasers, which not only confirm the presence of extremely compact and energetic regions but also trace the motions of gas with extreme precision. These masers act like natural beacons, marking sites of intense star formation or accretion phenomena that are otherwise hidden. Beyond individual sources, the continuum radio emission of ARP 220 tells us about the total synchrotron radiation produced by cosmic ray electrons spiraling in magnetic fields. This emission is diffuse and extended, often following the morphology of the galaxy's starburst regions. The strength and shape of the continuum allow astronomers to estimate magnetic field strengths, cosmic ray densities, and the efficiency of particle acceleration in supernova shocks. Crucially, Radio observations also help test the balance of power between star formation and black hole activity in ARP 220. While both processes can produce radio emission, they leave behind distinct signatures. Starburst-related radio emission tends to be extended and correlates with far-infrared output, due to the well-known radio-infrared correlation in star-forming galaxies, whereas AGNs often produce compact, high-brightness regions or jets. Although ARP 220 lacks clear large-scale jets like those seen in radio galaxies, compact, high-luminosity radio cores in its western nucleus have raised suspicions about the presence of a buried AGN, and this question remains active, with radio astronomy at the forefront of the investigation. The breadth of what we've learned about ARP 220 through radio astronomy also demonstrates how crucial multi-wavelength approaches are. What we can't see in the optical, we unveil in the radio. What we miss in the X-rays due to dust obscuration, we recover in millimeter lines. And what we suspect from theory, we often confirm through these long, dust-piercing wavelengths. It is thanks to radio astronomy that ARP 220 has transformed from an obscure, overly bright dot on an IRIS survey into a landmark galaxy, a prototype for studying extreme starbursts, dusty mergers, molecular inflows, and possibly even dual black hole evolution. Without radio telescopes, we would still be in the dark, literally and figuratively, about what is arguably the most chaotic, luminous, and fascinating object within 300 million light-years of Earth. As radio instruments continue to improve, with arrays like the Square Kilometer Array, SKA, and next-gen VLBI systems, the resolution, sensitivity, and depth of our observations will only get better. We will soon be able to detect even fainter supernova remnants, map smaller-scale gas flows, and perhaps, finally, image the event horizon region of any lurking black holes within ARP 220. So, in the war against cosmic opacity, radio waves are our secret weapon. They reveal what dust tries to hide. They trace energy where light fails. And in ARP 220, they've built the scaffolding for nearly everything we know about this galactic inferno. While radio astronomy has long served as our window into the hidden chaos of ARP 220, it is the ALMA Large Millimeter/Submillimeter Array, ALMA, that has elevated that view into something truly transformative. Sitting high in the Chilean Andes at an altitude of 5,000 meters, ALMA is uniquely positioned to observe the coldest and densest components of the universe with unprecedented clarity. And for a galaxy like ARP 220, where almost all of the drama is cloaked in thick clouds of gas and dust, this clarity has been nothing short of revolutionary. ALMA operates in the millimeter and submillimeter wavelengths, a critical range for detecting the emission from cold molecular gas, the raw material for star formation. Unlike optical and even standard radio telescopes, which struggle to detect and resolve complex gas structures in heavily obscured regions, ALMA is exquisitely sensitive to the spectral lines emitted by key molecular species such as carbon monoxide, CO, hydrogen cyanide, HCN, formilium, HCO, and other dense gas tracers. These molecules act as cosmic thermometers and barometers, providing insight into the temperature, density, and motion of the gas within the galaxy. In ARP 220, ALMA has revealed that the molecular gas isn't just present, it's concentrated, turbulent, and extraordinarily dense. Most of it resides in the central kiloparsec, forming an extreme environment where star formation proceeds with reckless abandon. Observations have shown that the two nuclei, each the remnant of the progenitor spiral galaxies, host compact, rotating disks of gas, both of which are crammed with mass on a scale rarely seen outside the most active galactic cores in the universe. Each of these nuclear disks spans only a few hundred light-years, yet contains the mass of several billion suns. These disks are thick, warm, and rotating at tremendous velocities, signatures that hint not only at the gravitational influence of massive stellar clusters, but also possibly supermassive black holes embedded within them. ALMA has traced the kinematics of these rotating structures in stunning detail, allowing astronomers to model the mass distribution, rotation curves, and turbulent pressures that shape their dynamics. Perhaps most strikingly, ALMA has uncovered massive molecular outflows emerging from the core of ARP 220, jets of cold gas blasting out from the nuclei at speeds of hundreds of kilometers per second. These outflows are direct evidence of feedback, the process by which star formation or black hole activity injects energy back into the interstellar medium, disrupting further collapse and thereby regulating the pace of galactic growth. In ULIRG 220, both nuclear regions appear to be driving such outflows, suggesting a dual feedback mechanism likely fueled by a combination of stellar winds, supernovae, and possibly AGN activity. These molecular outflows are incredibly rich in information. By analyzing the velocity profiles of specific emission lines, particularly high-density tracers like HCN, ALMA can differentiate between inflows feeding star formation, turbulent rotational motion, and outflows blasting material away. The balance between these flows tells us about the galaxy's evolutionary stage. In ULIRG 220, this balance is clearly shifting. While inflows continue to funnel gas into the nuclei, the growing strength of the outflows indicates that the starburst may be approaching its peak, and the system may soon begin a slow decline as gas is either consumed or ejected. One of ALMA's unique strengths is its ability to detect not just common molecules, but also complex organic compounds. In ULIRG 220, molecules like methyl cyanide, CH3CN, acetaldehyde, CH3CHO, and even formamide, NH2CHO, have been detected, building blocks of prebiotic chemistry. This raises fascinating questions. Can such complex molecules survive in environments as extreme as ULIRG 220's nucleus? Are they formed there, or do they arrive via merging clouds? These are not just chemical curiosities. They speak to the universality of organic chemistry and may have implications for how life's ingredients are distributed across the cosmos. Even the dust itself, a nemesis in other wavelengths, becomes a source of knowledge with ALMA. Cold dust emits strongly at submillimeter wavelengths, and by mapping this emission, astronomers can construct detailed dust temperature maps, estimate gas-to-dust ratios, and determine obscuration depths. In ULIRG 220, these maps reveal that the optical depths are staggeringly high, even at millimeter wavelengths in some regions. The western nucleus, in particular, appears to be wrapped in a shroud of dust so thick that it remains opaque in the submillimeter regime, an almost unheard-of characteristic that reinforces the idea that something extraordinarily dense lies at its core. ALMA's high-resolution imaging has also illuminated the fragmented structure of the gas and dust within each nucleus. Rather than being smooth, continuous disks, these regions are filled with clumps, filaments, and cores, likely the sites of massive star cluster formation. Each of these dense clumps could birth thousands of stars, many of them short-lived, massive ones that will soon go supernova, contributing further to the radio emission seen in VLBI observations. This clumpy, hierarchical structure may be key to understanding how the most intense starbursts in the universe are organized, and how energy and momentum cascade through such violent systems. Furthermore, ALMA has revealed subtle temperature gradients in the dust and gas, with warmer components closer to the central engines and cooler structures extending outward into the molecular disk. These gradients can be used to model radiative transfer processes, how energy moves through the system, and to determine whether the dominant source of heating is from embedded young stars, shocks, or obscured AGN activity. In ULIRG 220, there is evidence for all three: stars, supernovae, and black holes working in concert to heat and shape their environment. In terms of velocity structure, ALMA's spectral resolution has been instrumental in detecting non-circular motions in the gas, including radial flows, asymmetric turbulence, and signs of disrupted or warped rotation. These features support the idea that ULIRG 220 is still settling from the merger, and that its internal equilibrium has yet to be restored. The gas is not yet in stable orbits. It is in flux, inflamed, and unstable, a galaxy still forming its final shape. Taken together, ALMA's observations are not just a technical achievement. They are a cosmic narrative, telling the story of a galaxy in transformation. They show us the raw, physical conditions of a stellar furnace mid-burn, a galactic collision unfolding in slow motion, and a symphony of forces, gravity, radiation, turbulence, chemistry, playing out on a grand, unrelenting scale. And yet, ALMA's view is not final. The galaxy continues to evolve, The dust continues to obscure. The stars continue to explode. But thanks to instruments like ALMA, we now have a front-row seat to it all, a millimeter-wave microscope focused on one of the most energetic, extreme, and instructive laboratories in the nearby universe. If radio and millimeter observations like those from ALMA have peeled back the outer layers of ARP 220's chaos, then the James Webb Space Telescope, JWST, promises to look even deeper, to probe the warm dust, buried stars, and embedded black holes that still remain cloaked from our view. The JWST, a marvel of infrared engineering, was designed precisely for challenges like this, to penetrate cosmic dust, to uncover hidden processes, and to answer the questions that galaxies like ARP 220 have stubbornly refused to give up for decades. While ALMA has mapped the cold molecular gas and dust with exquisite detail, JWST's strength lies in its ability to observe mid- and near-infrared wavelengths, which are ideal for detecting warm dust, nascent stars, and hot gas in regions too obscured for visible light to reach. For ARP 220, arguably the most dust-enshrouded galaxy in the nearby universe, this makes JWST an essential new tool in the quest to understand its interior. Already, early JWST observations of dusty, merging galaxies have proven revolutionary. Its mid-infrared instrument, MIRI, and near-infrared spectrograph, NIR-SPEC, are revealing previously unseen populations of stars, detailed structures in gas and dust, and even signs of embedded active galactic nuclei, AGNs, in galaxies where none were definitively confirmed before. ARP 220, with its thick, nearly opaque nuclear regions and ambiguous signs of AGN activity, is a prime candidate for such investigation. With JWST, astronomers will be able to map the warm dust emission that blankets the two nuclei, separating out temperature components and revealing dust heating mechanisms. By identifying spectral features, such as those from polycyclic aromatic hydrocarbons, PAHs, researchers can trace regions of active star formation, since PAHs tend to form around young, hot stars. The presence, absence, or suppression of these features can also help distinguish between starburst-driven and AGN-driven activity. In ARP 220's western nucleus in particular, the dust is so thick that not even ALMA could fully peer into its center. There are signs of compact hot dust and faint X-ray emission, potential indicators of a hidden AGN, but nothing definitive. JWST can push further. Through the silicate absorption features at 9.7 and 18 microns, and the shape of the continuum in the 5 to 28 micron range, MIRI can detect buried AGNs even when they contribute only a fraction of the total infrared light. A rising power law continuum, for example, is often a telltale sign of black hole accretion, especially when paired with suppressed PAH features. Moreover, JWST can dissect the stellar populations of the two nuclei. In optical wavelengths, starlight from ARP 220's center is almost completely absorbed or scattered. But in the near-infrared, JWST can begin to separate old stellar light from the newly forming clusters, estimate their ages, metallicities, and even determine how many generations of stars have already formed since the galaxies began merging. This is key to understanding the timeline of the starburst, when it began, how long it has been sustained, and how it might end. Additionally, JWST will have the sensitivity to detect embedded superstar clusters, compact, young groups of massive stars that are believed to be ubiquitous in starburst galaxies like ARP 220 but are difficult to resolve in crowded, dusty regions. These clusters could be the progenitors of future globular clusters or the seeds of galactic bulges. By studying their sizes, masses, and distributions, we can learn how massive cluster formation differs in extreme environments compared to calmer galaxies like our own. JWST will also contribute to our understanding of gas flows and feedback mechanisms. With its spectroscopic capabilities, the telescope can measure ionized gas tracers such as the 2, S3, and O4, which help determine the radiation fields and excitation mechanisms inside the galaxy. These lines are crucial in diagnosing shock heating from supernovae, photoionization from massive stars, and potential ionization cones from AGNs. In a system as extreme as ARP 220, it's likely that all three mechanisms are present, overlapping and competing, and JWST can finally provide the resolution and sensitivity to tease them apart. Crucially, JWST can observe molecular hydrogen emission lines, especially in the near and mid-infrared. These lines trace warm molecular gas, distinct from the cold gas seen by ALMA. Warm molecular gas can be excited by shocks, UV radiation, or turbulent mixing layers, and by studying its distribution, JWST will help identify outflow regions, stellar wind zones, and interaction fronts between colliding gas clouds. Understanding this warm gas is vital, as it often acts as an intermediate stage between dense star-forming clumps and diffuse interstellar matter, marking where the galaxy is transitioning energy into different forms. But perhaps most enticing is the possibility of JWST capturing rare infrared transients, brief events like supernovae or accretion flares from black holes, that would be invisible in other wavelengths. With its sensitivity and deep field imaging, JWST might catch a young, still enshrouded supernova remnant, or the first infrared signature of a tidal disruption event, where a star is shredded by a black hole's gravity. These transient phenomena are key to understanding feedback, energy injection, and the life cycle of massive stars in environments dominated by extreme starburst conditions. And let's not forget the broader context. JWST will allow us to compare up 220 to similar galaxies at high redshift. Many of the galaxies JWST is designed to observe in the early universe are distant analogs of ARC-220, dusty, ultraluminous infrared galaxies experiencing violent starbursts, likely triggered by mergers. With ARC-220 as a local benchmark, JWST's distant galaxy observations become more interpretable. Conversely, by seeing high redshift galaxies in their formative years, JWST will provide clues about ARC-220's past, linking its current chaotic state to a broader cosmic timeline. In sum, JWST will not merely complement the radio and millimeter observations of ARC-220. It will bridge the gaps between them, bringing the buried star clusters, the potentially active black holes, the warm dust and gas, and the rich chemical signatures into full view. It will clarify what is still uncertain, challenge what we thought we knew, and reveal the layers of structure and activity still hidden in the galactic shadows. ARC-220, long a mystery buried in infrared light, is about to be exposed to the most advanced infrared telescope humanity has ever built. And when JWST turns its golden eyes to that furnace of dust and stars, it may finally show us what lies at the true heart of one of the most chaotic galaxies in the local universe. There is a strange beauty in cosmic decline, a quieting after chaos, a slow dimming of the galactic furnace. In the case of ARC-220, while the galaxy remains one of the most luminous and dynamic objects in the nearby universe, some models suggest that its explosive starburst may have already passed its peak. What we may be witnessing now is not the height of the storm, but its fading roar, a phase of gradual decline, where the immense energies unleashed by the merger begin to disperse, and the conditions that fueled hyperactive star formation start to wane. This idea stems from a combination of observational data and simulations that track the life cycle of merging galaxies and their central starbursts. When two spiral galaxies like those that formed ARC-220 collide, gravitational forces funnel vast quantities of cold gas into the central regions. This sudden compression of gas ignites intense star formation, particularly in compact nuclear disks where densities reach critical thresholds. In ARC-220's case, the result was a furious birth rate of stars, hundreds of times greater than that of the Milky Way, leading to the prolific population of supernova remnants, radio sources, and superstar clusters we observe today. But such a violent starburst is unsustainable over long timescales. There is only so much cold gas available, and only so many ways it can be converted into stars before either being consumed or expelled. Star formation is not a limitless process. It's bound by the laws of feedback and depletion. Massive stars, while short-lived, explode as supernovae, injecting energy into their surroundings, stirring the interstellar medium, and often blowing apart the very clouds from which new stars might have formed. In essence, these stars burn out fast and burn out bright, and in doing so, disrupt future generations. Observational evidence hints that this disruption may now be occurring in ARC 220. ALMA data, combined with high-resolution infrared and radio studies, shows signs of molecular outflows, streams of cold gas being ejected from the nuclear regions at high velocities. These outflows, possibly driven by the combined effects of supernova feedback, stellar winds, and maybe even embedded AGN activity, are powerful enough to remove large amounts of star-forming material from the galaxy's core. If these processes continue, they could choke off the fuel supply that sustains the starburst. The spatial distribution of star formation within ARC 220 also supports the past the peak narrative. While the two nuclei still contain active regions, some observations suggest that the most extreme bursts occurred several million years ago and are now cooling and dispersing. Infrared maps show concentrated warm dust in older starburst zones, while spectral signatures of freshly ionized gas have begun to wane. Supernova activity is still occurring, but may no longer match the staggering rates seen in earlier epochs. In terms of stellar population synthesis models, analyses of ARC 220's light, particularly in the infrared, suggest that a significant portion of its current luminosity is coming not just from newly formed stars, but from evolved, aging populations. These stars, often massive blue giants or red supergiants, dominate the infrared light output but represent a generation of stars that formed millions of years ago, during the peak of the merger-induced frenzy. Their presence implies that the initial burst may already be declining, transitioning from a period of creation to one of aftermath. Further supporting this, models of galactic evolution based on simulations of mergers, particularly those that mimic the conditions observed in ARC 220, indicate that such intense starbursts are typically short-lived, lasting around 100 to 300 million years at most. After this phase, galaxies enter a more quiescent mode, where star formation continues but at a much slower rate. Gas is either consumed or expelled, the central regions stabilize, and black holes may begin to dominate the energetic output, if they haven't already. The notion that ARC 220 is winding down doesn't mean it's quiet. Far from it. Even in decline, it is still a furnace of energy, producing stars and ejecting gas, glowing brightly in the infrared, and churning with molecular turbulence. But it does suggest that the galaxy is evolving, moving from the chaotic crescendo of collision toward a more stable, mature state. Over the next few 100 million years, if current trends continue, the two nuclei will likely merge completely, the remaining gas will settle or be blown out, and the galaxy will transition into a more elliptical structure, perhaps resembling the massive, red, and dead elliptical galaxies we see in the centers of galaxy clusters today. Interestingly, this transitional phase offers unique scientific opportunities. Galaxies like ARC 220 that are post-starbursts but still active help bridge our understanding between young, star-forming systems and older, passive galaxies. They show us how energy from stars and black holes shapes the gas reservoir, how star formation shuts down, and how mergers sculpt the final morphology of galaxies. Studying ARC 220 in this phase is like observing a phoenix after its flames, catching the tail end of a cosmic firestorm before it cools into silence. It's worth noting that winding down doesn't mean uniformly fading. Some regions of ARC 220 may flare back up, especially if pockets of dense gas survive the current outflows. New stars may still form in isolated clusters. Interactions between the nuclei, tidal forces, or even minor infalling companions could reignite activity. But these would likely be smaller, more localized bursts, unable to replicate the scale and intensity of the peak event that likely occurred tens of millions of years ago. We are witnessing, then, not the end, but the denouement, the graceful deceleration after a furious sprint, a galaxy catching its breath after a cataclysm. It's a phase filled with echoes, the echoes of supernovae, of consumed gas, of colliding black holes not yet merged. And as ARC 220 continues to cool, settle, and fade from its once blistering brilliance, it will do so carrying the legacy of its violence, the stellar relics of a cosmic upheaval, and perhaps, the seeds of quiet galaxies to come. It's almost poetic that when we look at ARC 220, this wildly chaotic, dust-choked, star-forming inferno, we may be staring into a mirror of our galaxy's distant future. As violent and alien as it appears now, ARP 220 might one day reflect the fate of our own Milky Way, when it collides with its nearest massive neighbor, the Andromeda Galaxy, approximately 4 billion years from now. The comparison is not merely dramatic, it's scientifically grounded. The gravitational ballet we witness in ARP 220 today could be a preview of the grand merger that awaits us, with all the accompanying beauty and destruction. Let's start with what we know. The Milky Way and Andromeda are on a collision course. Observations show that Andromeda is moving toward us at about 110 kilometers per second. Their mutual gravitational attraction will eventually draw the two spiral galaxies into a direct collision, distorting both in the process and culminating in a full merger over several billion years. Although the stars themselves are unlikely to collide directly due to the vast distances between them, the gas and dust in each galaxy will interact violently, triggering shocks, turbulence, and most notably, a galactic starburst. In that way, the Milky Way-Andromeda merger will likely mimic the early stages of ARP 220. Gas clouds will compress as gravitational tides funnel material toward the centers of both galaxies. The result? A furious epoch of star formation, possibly thousands of new stars forming every year. This is precisely what we believe happened in ARP 220. The gas-rich disks of its two progenitor galaxies collided, their interstellar media crashing into each other like waves, creating high-density environments ripe for star formation on an ultraluminous scale. If the Milky Way and Andromeda each bring in their full supply of gas, and some simulations suggest they will, their eventual union could resemble a younger ARP 220. Star clusters may begin forming at rates far above current norms, and in the galactic cores, we might see the creation of double nuclear disks, just as we do in ARP 220. Over time, this duality would blur, forming a dense core packed with superstar clusters, aging giants, and the remnants of the earliest collisions. And what about the black holes? Both the Milky Way and Andromeda host supermassive black holes at their centers. The Milky Way's Sagittarius A weighs in at about 4 million solar masses, while Andromeda's central black hole is estimated to be over 100 million solar masses. When the two galaxies merge, these black holes will begin a long gravitational dance. At first, they'll orbit each other at increasing speed, radiating gravitational waves as they draw closer. Eventually, they may merge into a single, even more massive black hole, releasing one of the most energetic bursts of gravitational radiation in the observable universe. This exact scenario is one of the predictions for ARP 220's future, that its twin nuclei, each suspected to contain a buried supermassive black hole, will eventually merge. So when we look at ARP 220 today, with its still distinct dual cores and surrounding turmoil, we're witnessing a step in a process our galaxy may undergo itself. It's not just a galaxy, it's a time machine, a glimpse into what the sky might look like from Earth, assuming anyone's still here to see it, in a few billion years. The transformations won't stop at starbursts and black hole mergers. As the galactic cores settle, and the gas is gradually consumed or blown away by feedback processes, the remnants of the Milky Way-Andromeda collision will no longer resemble spirals. Instead, they will likely form a massive elliptical galaxy, similar to what ARP 220 may eventually become. These galaxies are often larger, redder, and less gas-rich, dominated by older stars. Once the fireworks die down, the newly formed elliptical settles into a quieter phase of evolution, cooling, aging, and slowly dimming over time. Simulations predict that this eventual merged galaxy, sometimes dubbed Milkomeda, will shine brightly in its youth, but over billions of years, will become more quiescent, much like what we expect for ARP 220 as its starburst fades. By studying ARP 220 now, we can learn what mechanisms will drive this transformation, how gas is expelled by supernovae, how feedback suppresses further star formation, and how structures like dust lanes and tidal tails dissipate over time. There are also cosmic consequences for the surrounding galactic environment. Just as ARP 220 is not isolated, it resides in a field with other galaxies that may be influenced by its gravity. The Milky Way-Andromeda merger will also have gravitational consequences for nearby companions, like the Triangulum Galaxy, M33. In fact, some simulations suggest M33 might be drawn into the merger itself, potentially creating a triple galaxy collision, adding more fuel and complexity to the process. Similar minor mergers might have shaped the outer structure of ARP-220, and could help explain asymmetries in its extended molecular gas halos and dust arms. And there's another aspect: cosmic time. What we see in ARP-220 today is how it looked 250 million years ago, the time it took light to travel from there to here. In cosmic terms, that's roughly when dinosaurs first began dominating Earth. By observing galaxies at various distances, and thus at various stages in their evolution, we're effectively looking forward and backward in time. ARP-220 sits in a sweet spot, close enough to observe in great detail, but far enough to represent a significantly later stage of merger evolution than the Milky Way Andromeda collision has yet reached. In other words, we are watching a version of our own destiny unfold in real time. The physics is the same: gravity, gas dynamics, stellar evolution, feedback loops. The only differences are timing and proximity. And that makes ARP-220 more than an object of study. It's a cosmic rehearsal for what lies ahead. It reminds us that galaxies are not static. They are living, evolving systems, and collisions, far from being rare accidents, are a fundamental part of that life cycle. The night sky of the far future will bear little resemblance to the one we know now. Constellations will distort. Tidal streams will streak across the heavens. The merged Milkometa will dominate the sky, first as two bright spiral galaxies drifting together, then as a single, glowing behemoth with a complex heart and a halo of ancient stars. In its center may sit a furnace like ARP-220's, bright in infrared, rich with superstar clusters, maybe even a dense population of supernova remnants, echoes of creation following the cosmic chaos of collision. One of the most profound and beautiful truths about galaxies like ARP-220 is that out of their violence comes creation. What seems at first glance like chaos, a supernova exploding, a starburst burning through its gas, shockwaves crashing through molecular clouds, is actually part of a cosmic recycling process, an ongoing cycle that forges the ingredients of life and spreads them across space. In ARP-220, this process is occurring on a truly epic scale. Its supernova-rich core is not just a graveyard of stars, it's a factory of elements, crafting the building blocks of planets, atmospheres, and potentially life itself. To understand the recycling at play, we must start with stellar nucleosynthesis. Stars are natural alchemists. In their cores, through nuclear fusion, they convert hydrogen, the simplest element, into helium, and then, in more massive stars, into progressively heavier elements like carbon, nitrogen, oxygen, silicon, and eventually iron. But these heavy elements, known collectively as metals in astronomical terms, don't just stay locked inside their stellar furnaces. They're only released into the galaxy when the stars die, and the most dramatic deaths come in the form of supernovae. In ARP-220, where massive stars are being born in dense clusters at extraordinary rates, supernovae are common and frequent. These titanic explosions do more than just punctuate the lives of stars. They enrich the interstellar medium with the heavy elements those stars created. The remnants of these explosions, hot clouds of gas, shock fronts, expanding bubbles, carry metals outward into surrounding space. And this is where the magic happens. The elements ejected from dead stars are the raw materials for new ones. In fact, the gas and dust clouds that form new stars in ARP-220 are now significantly metal-enriched compared to the original material from the colliding galaxies. This enrichment is essential. Without it, planets like Earth, composed of silicon, iron, magnesium, carbon, and oxygen, couldn't exist. Neither could water, atmospheres, or the organic molecules that form the basis of life. In this way, every supernova in ARP-220 is not only a death but a gift to the future, seeding the galaxy with the potential for complex systems. Over time, the enriched material from these explosions becomes part of new generations of stars. Some of that gas cools and contracts into molecular clouds, where gravity takes over and initiates the formation of new stars. The process is often enhanced by the very supernova shockwaves that expelled the metals in the first place, triggering star formation by compressing surrounding gas. In this way, Supernovae are both destroyers and creators, closing one loop and beginning another. In ARP 220, this cycle is operating at an extreme scale. The number of supernova remnants detected in its core, over 200, is not only a testament to the intense starburst underway but also a signal that the galaxy is becoming a cosmic crucible. Every one of those remnants represents a massive star that lived fast and died young, pouring its enriched interior into the surrounding gas. Multiply that by hundreds, perhaps thousands of stars, and you begin to get a sense of how deeply ARP 220 is reshaping its own chemistry. This process of enrichment is not uniform. The central regions of ARP 220, those dense, dusty nuclear disks, are likely to be the most metal-rich, having hosted the largest number of massive star deaths. But as outflows carry dust and gas away from the nuclei, they also transport metals into the galaxy's outer regions, potentially mixing with less enriched gas. Over time, this leads to a gradient in metallicity, from the core to the outskirts, a feature seen in many galaxies and one that helps astronomers trace the history of star formation and feedback over time. There's also a broader galactic implication. As stars form from enriched gas, their spectral signatures change. New stars in ARP 220 will bear the fingerprints of past generations. The ratio of iron to hydrogen, or oxygen to carbon, will be higher. This allows scientists to track the evolution of the galaxy by studying the light of its stars. In this way, ARP 220 writes its chemical autobiography in starlight. Even the dust in ARP 220 is part of this recycling loop. Dust grains form in the cooling ejecta of supernovae and the winds of dying stars. These grains, made of carbon, silicon, and iron, are the seeds around which planets eventually form. In ARP 220, thick clouds of dust now blanket its core, hiding much of the action from optical view but also preserving and transporting the elements forged in fire. Some of that dust will survive the turbulent feedback processes and one day collapse with gas into new solar systems, rich with the potential for solid worlds. Though we have no evidence of planetary systems in ARP 220, it's too distant, too obscured for such detections. It's likely that planetary formation is already underway in some of its more stable, post-starburst zones. The necessary ingredients are there: heavy elements, dust grains, and time. And perhaps, deep in some nascent system, a rocky world is forming, bathed in the light of a second or third generation star, its composition already bearing the ashes of supernovae long gone. On a larger scale, ARP 220's ongoing enrichment contributes to our understanding of galaxy evolution across cosmic time. In the early universe, galaxies were metal poor, formed from pristine hydrogen and helium left over from the Big Bang. As time passed, successive generations of stars enriched the cosmos. Galaxies like ARP 220 show how this enrichment can be supercharged by mergers and starbursts. They act as engines of chemical evolution, dramatically accelerating the production and distribution of metals. This is part of why astronomers are so interested in galaxies like ARP 220, not only for their beauty and complexity but because they demonstrate how the raw material for life is made and spread across the universe. The calcium in your bones, the iron in your blood, the oxygen in your lungs, all of it was forged in stars and scattered by supernovae. Galaxies like ARP 220 are where that story begins. So when we look at ARP 220, with its dense, dusty core, its shockwaves, its storm of dying stars, we're seeing more than a galactic wreck. We're seeing a forge, a crucible, a place where the past dies so the future can live, where death becomes creation, and where the elements of life are born in fire, scattered by wind, and reassembled into something new. Ultraluminous infrared galaxies, or ULIRGs, like ARP 220, are not just cosmic curiosities. They are powerful beacons that shine across the fabric of space and time, offering astronomers a rare opportunity to study the processes of galaxy formation and evolution in the distant universe. Their immense infrared brightness, caused by the re-radiation of starlight by dust, allows them to be seen even when they are deeply embedded in dense clouds that would otherwise obscure them in visible light. In this way, ULIRGs act like searchlights piercing through the cosmic night, illuminating the mechanics of how galaxies grow, merge, ignite, and transform. ARP 220, as one of the closest and best studied ULIRGs, serves as a benchmark for interpreting similar galaxies at higher redshift. That is, galaxies that are much farther away and thus observed as they were in the early universe. Due to the expansion of the universe, the light from these distant galaxies is redshifted, meaning that their emitted light is stretched into longer wavelengths, often shifting visible and ultraviolet light into the infrared. This makes infrared observations critical for probing the early stages of galaxy formation, and it's here that ULIRGs, blazing in the infrared, play a crucial role. When we observe ULIRGs at great distances, we are looking back in time, often billions of years, to when the universe was much younger and galaxies were in the process of assembling. These distant ULIRGs are believed to be merging systems undergoing intense starbursts, much like ARP-220, and by comparing the two, we can draw connections between local phenomena and early cosmic history. In this way, ARP-220 becomes a kind of time machine, a detailed, nearby example of processes that shaped the first massive galaxies. The importance of ULIRGs as cosmic beacons was especially apparent with infrared space telescopes like Spitzer, Herschel, and more recently JWST, which have peered into the early universe and found large populations of dusty, star-forming galaxies at high redshift. Many of these galaxies are astonishingly luminous, forming stars at rates of several hundred to even 1,000 solar masses per year. Because of their extreme infrared output, astronomers began calling them submillimeter galaxies, SMGs, a population of early, massive, starbursting systems that seem to represent a crucial phase in galaxy evolution. ARP-220 is often used as a template for interpreting the emission properties, dust content, and star formation rates of these distant galaxies. These high redshift ULIRGs are thought to play a key role in the buildup of massive elliptical galaxies, many of which are already in place just a few billion years after the Big Bang. This implies that ULIRGs are rapid growth engines, galaxies that form the bulk of their stars in quick, intense bursts. The mechanisms behind this explosive activity are similar to what we see in ARP-220, major mergers, where two gas-rich galaxies collide, compressing their gas into dense pockets that fuel runaway star formation. By studying ARP-220 in fine detail, we gain insights into feedback processes, black hole growth, stellar cluster formation, and dust production, all of which are central to modeling how galaxies evolved in the early universe. In fact, some models suggest that nearly half of the star formation in the early universe was hidden by dust and only detectable in the infrared. Without infrared observations, we would miss a substantial fraction of the activity that shaped the cosmos. ARP-220, glowing brilliantly in the infrared yet almost invisible in optical light, is a dramatic example of how misleading a galaxy's visible light profile can be. Its total infrared luminosity exceeds 10 superscript 1 superscript 2 times the luminosity of the Sun, qualifying it as an ULIRG, and reminding us that much of the universe's most energetic processes are hidden from view unless we look at the right wavelengths. Furthermore, ARP-220 also provides a calibration point for converting infrared luminosity into star formation rates. Because we can study ARP-220 up close, measure its gas content, count its supernova remnants, and estimate its cluster populations, we can validate and refine the formulas used to estimate the star formation rates of more distant, less resolvable galaxies. This is especially important for large surveys conducted by telescopes like ALMA and JWST, which are now detecting thousands of dusty, infrared bright galaxies at redshifts of 3, 5, or even 7, when the universe was just a few 100 million years old. In a sense, ULIRGs are the tip of the cosmic iceberg. They may be rare today, only a few dozen exist in the nearby universe, but in the early cosmos, they were far more common. Their infrared light still travels to us across billions of light years, acting as a record of ancient starbursts, written in the long, cool glow of dust. And because light from distant objects is redshifted into the infrared, ULIRGs become even more useful the further we look. They remain bright while other galaxies fade into invisibility. ARP-220 and galaxies like it also help us understand the connection between galactic mergers and active galactic nuclei, AGN. Many high redshift ULIRGs are found to host AGNs, supermassive black holes actively accreting matter and emitting powerful radiation. But detecting these AGNs is difficult, especially when obscured by dust. In ARP-220, The presence of a buried AGN is still debated. If confirmed, it would help astronomers refine the diagnostics used to identify AGNs in more distant, unresolved systems. This has implications for our understanding of coevolution, how the growth of galaxies and black holes are intertwined. Finally, ULIRGs like ARP-220 are also key to tracing the dust content of the universe over time. Dust plays a fundamental role in cooling gas, forming stars, and obscuring light. By studying the dust temperatures, masses, and compositions in nearby ULIRGs, astronomers can better estimate how much dust exists in the early universe, how it forms, and how quickly it is destroyed or recycled. This, in turn, helps build more accurate models of galaxy formation, especially during the so-called cosmic noon, when the universe experienced its peak of star-forming activity. So, while ARP-220 may seem like a chaotic outlier, it is in fact a cosmic cornerstone, a local laboratory for understanding the distant universe. Its thick dust, roaring starbursts, dual nuclei, and molecular outflows are not just exotic features of a single galaxy. They are recurring themes in the story of cosmic evolution. As our infrared telescopes scan the depths of space, discovering galaxies formed in the universe's first billion years, ARP-220 continues to teach us how to interpret those ancient lights, and how to read the dusty pages of the universe's earliest chapters. ARP-220 is, in every sense, a violent laboratory, not in the sterile, controlled way a traditional lab might be, but in the chaotic, explosive, and cosmic way that only a galactic collision can provide. It is a living experiment in the universe's most intense phenomena, a place where the laws of physics are pushed to their limits, where matter and energy interact under conditions rarely replicated elsewhere, and where the very building blocks of galaxies are being torn apart and reassembled before our eyes. ARP-220 is not just a galaxy, it's a natural collider, a vast testing ground for extreme physics, where every explosion, shockwave, and turbulent swirl of gas reveals something fundamental about how galaxies are born, evolve, and sometimes destroy themselves in the process. To begin with, ARP-220 offers a unique window into the physics of starburst activity. While many galaxies, including the Milky Way, form stars, few do it on the industrial scale seen in ARP-220. The star formation rate in its nuclear regions is hundreds of times higher than what's observed in ordinary spiral galaxies. This allows astronomers to study how gas cools and collapses into stars under extreme pressure and density, conditions vastly different from those in our galactic backyard. The molecular gas in ARP-220's center reaches densities that exceed 10 particles per cubic centimeter, levels that would collapse quickly under gravity if not counterbalanced by thermal pressure, turbulence, and magnetic fields. Understanding this balance requires insights from hydrodynamics, plasma physics, and radiative transfer theory, making ARP-220 a case study in multidisciplinary astrophysics. But star formation is just one layer of the violence. There's also the relentless feedback from young, massive stars. These stars emit strong ultraviolet radiation, stellar winds, and ultimately explode as supernovae. The energy input from these processes stirs the surrounding interstellar medium into a storm of motion. In ARP-220, the result is an environment rich with shocked gas, turbulent eddies, and non-thermal radiation, all of which can be studied using high-resolution spectral observations. These feedback mechanisms influence the future of the galaxy, determining where new stars will, or won't, form and how quickly gas is expelled into the halo or lost into intergalactic space. Then there's the dynamics of the merger itself, a process that plays out over hundreds of millions of years. The interaction between the two original spiral galaxies created enormous gravitational tidal forces, warping their disks, stripping material into elongated tails, and funneling matter into the galactic centers. ARP-220 still carries the fingerprints of this violence. Its double nuclei, separated by a mere 1,200 light-years, are caught in the final stages of orbital decay, spiraling slowly toward one another under the influence of dynamical friction. The distribution of stars and gas in the surrounding regions is asymmetric and disturbed, as one might expect from two galaxies tearing into each other's structure. These merger dynamics are key to understanding how massive elliptical galaxies form, since mergers are believed to be the primary pathway through which large galaxies grow over cosmic time. ARP 220 is a rare opportunity to study a major merger in its active phase, when the two progenitors are still distinguishable, and their individual dynamics can be disentangled. Computer simulations, using N-body and hydrodynamic modeling, are often tested against galaxies like ARP 220 to validate their predictions. This helps researchers determine how long such mergers take, what structures they leave behind, and how the energy of colliding components gets redistributed into star formation, black hole growth, and kinetic motion. Even the interstellar medium, ISM, in ARP 220 is a study in extremes. Observations show that the temperature, density, and chemical composition of the ISM vary wildly from one region to another. The central kiloparsec contains not only hot, X-ray emitting plasma from supernovae, but also dense molecular clouds observed in CO, HCN, and other tracers using ALMA and other millimeter-wave observatories. The conditions are ripe for the formation of complex organic molecules, and indeed, molecules like methanol, formaldehyde, and hydrogen cyanide have been detected in ARP 220's core. In this way, ARP 220 also functions as a chemical laboratory, revealing how complex chemistry unfolds under pressure and in the presence of intense radiation fields. The compact star clusters forming in ARP 220's nuclear disks are also of particular interest. These clusters are among the most massive and dense young stellar systems ever observed. They form rapidly, in bursts, and their gravitational stability is still a matter of study. Are these protoglobular clusters? Could they survive to become part of the future elliptical galaxy's halo? These are the questions ARP 220 is helping us answer. Their evolution, survival, and feedback effects are all part of the broader story of how galaxies build up their stellar populations during and after violent mergers. Then there is the role of magnetic fields, an often overlooked aspect of galactic physics. In ARP 220, the interplay between intense radiation, dense gas, and supernova activity likely generates strong magnetic fields, which in turn influence gas dynamics, star formation efficiency, and the structure of molecular clouds. Polarization studies at radio and submillimeter wavelengths can reveal how these magnetic fields thread through the interstellar medium, guiding the motion of charged particles and influencing how cosmic rays propagate through the galaxy. This opens a new dimension to our understanding of feedback and energy transfer within extreme systems. Importantly, ARP 220 also challenges our understanding of black hole accretion and obscuration. While the galaxy's extraordinary infrared output is mostly attributed to starbursts, some evidence suggests that one or both of its nuclei may contain heavily obscured active galactic nuclei, AGN. These AGNs, if confirmed, are among the most buried ever observed, their X-rays and UV radiation absorbed by columns of gas and dust so thick that only radio and infrared can hint at their presence. This makes ARP 220 an ideal subject for testing models of buried AGN, which are especially relevant for interpreting distant galaxies seen with JWST that may also host concealed black holes. How much energy is really coming from accretion versus star formation? How do we detect AGNs when even X-rays can't get out? ARP 220 pushes the limits of observational astrophysics in answering such questions. And then there's the future. ARP 220 is not static, it continues to evolve, and that evolution provides a long-term test of theories about post-merger relaxation, starburst quenching, and black hole mergers. We may be witnessing a galaxy in transition, one that will, over the next billion years, shed its chaotic outer regions, calm its central fury, and settle into a mature elliptical galaxy, dense, red, and old. Understanding this transformation in detail requires not only snapshots but time-based models, and ARP 220 provides the perfect case study to refine them. All told, ARP 220 is a living, breathing lab, a place where cosmic violence breathes insight. From the collapse of molecular clouds to the explosions of massive stars, from the spiraling of twin galactic cores to the whisper of hidden black holes, it is a galaxy that holds a mirror up to the universe's most extreme processes. Studying ARP 220 isn't just about understanding a single object. It's about decoding the universal forces that shape every galaxy, every star, and perhaps every planet. ARP 220 holds a title few galaxies can claim. It is utterly one of a kind in our cosmic neighborhood. While there are other ultraluminous infrared galaxies, ULIRGs, and even other merging systems, none that lie as close to Earth exhibit the same intense combination of luminosity, density, and chaotic internal structure that ARP 220 does. It stands as the brightest ULIRG within 300 million light-years, a gravitational and thermal masterpiece shaped by cosmic violence, wrapped in impenetrable dust, and burning with more energy than hundreds of billions of suns. To understand its uniqueness, we must look at the scale and extremes ARP 220 represents. Its total infrared luminosity, exceeding 10 superscript 1 superscript 2 solar luminosities, places it squarely in the ultraluminous class. But it's not just the raw power that sets it apart, it's where that power is coming from. ARP 220's energy is concentrated into its central kiloparsec, a region less than 3,200 light-years across. Within this tiny galactic core are two separate nuclei, hundreds of compact star clusters, thousands of massive stars, and over 200 detected supernova remnants. The density of activity in this area surpasses any other known nearby galaxy. In other galaxies, even starburst ones, this level of activity is often spread out over larger scales. But in ARP 220, the intensity per square light-year is staggering. It's like comparing a bonfire to a laser. Both produce heat, but one is wildly concentrated and far more extreme in impact. This central concentration of mass and energy gives rise to conditions, extreme pressures, rapid chemical evolution, intense radiation fields, that are incredibly rare in the local universe. That's why ARP 220 has become such a critical reference object. It's not just a bright infrared source, it's the brightest and most compact galactic furnace accessible to high-resolution, multi-wavelength studies. Even among other ULIRGs, ARP 220 stands out. Many ultraluminous galaxies are farther away, making detailed observations harder. Others may show strong infrared emission, but not the same combination of merger stage, double nuclei, high star formation rate, and radio-detected supernovae. Some ULIRGs harbor powerful active galactic nuclei, whereas ARP 220 is dominated by starburst activity, with AGN activity, if present at all, remaining deeply buried. This makes it a cleaner laboratory for studying the physics of extreme star formation, without the complicating effects of powerful central black hole jets or radiation dominating the signal. Moreover, no other nearby galaxy has such an extraordinary radio core, peppered with compact, unresolved sources that are believed to be supernova remnants. The sheer number of these remnants points to a supernova rate 100 times higher than that of the Milky Way. This number isn't theoretical, it's based on direct radio observations, which peer through the dense, dusty veil and reveal the explosive deaths of stars in nearly real time. There is no other galaxy close enough and luminous enough for astronomers to detect this many individual supernova remnants from Earth. This turns ARP 220 into a statistical gold mine, a singular opportunity to study the death rate of massive stars in an environment that mirrors the extreme star-forming galaxies of the early universe. The double nuclei of ARP 220 also offer something rare, a late-stage merger snapshot, where both cores are still present but deeply embedded, only 1,200 light-years apart. This is a brief and turbulent phase in the life of a galaxy merger, lasting perhaps just tens of millions of years, and we happen to be observing ARP 220 right now, in that window. The alignment of this timing, proximity, and observability makes ARP 220 an astronomical jackpot. It's like catching two supermassive black holes in the final laps of a gravitational waltz, hidden behind thick curtains, with only radio and infrared whispers to trace their steps. Then there's the question of chemical complexity. The molecular composition of ARP 220's core rivals the most chemically rich regions of the Milky Way. Scientists have detected a wealth of complex organic molecules in its central regions: methanol, formaldehyde, hydrogen cyanide, and more. The detection of these molecules in such an extreme environment challenges existing models of astrochemistry, raising questions about how molecules form, survive, and evolve under intense radiation, shocks, and turbulence. ARC-220 is helping push the frontier of understanding in this area as well. Not just what happens in gentle clouds, but what happens in the galactic crucibles where matter is remixed violently. In every wavelength, radio, infrared, submillimeter, even soft X-rays, ARC-220 behaves like a different beast entirely compared to more placid systems. Its optical signal is so heavily obscured by dust that it's barely visible at all. In the ultraviolet, it's practically silent. Yet in the infrared, it is blindingly loud. It shouts from the cosmos with a signature that is uniquely its own. Even JWST, designed to look at some of the faintest galaxies in the early universe, has pointed at ARC-220 as a local template, knowing that its secrets echo those of galaxies forming at redshift 5, 6, or even 10. Perhaps most telling of ARC-220's unique role is its repeated appearance in cosmological simulations and observational planning guides. Whenever researchers simulate the merger of massive spiral galaxies, test the limits of star formation feedback, or model the observables of high redshift dusty galaxies, ARC-220 comes up. Its data fills libraries. Its images are used in classrooms. Its radio signature, often displayed in vibrant reds and blues, adorns the covers of astrophysics journals. It's not just unique, it's foundational. And yet, for all this, ARC-220 remains incomplete. It's still evolving. Its central black holes, if indeed they are there, haven't merged yet. Its starburst, while potentially past its peak, hasn't died down completely. The chaos continues. Gas is still being funneled inward. Stars are still being born and dying. The merger, while far along, isn't over. And that gives astronomers time. Time to observe. Time to refine their instruments. Time to watch the transformation unfold, like a slow-motion detonation of galactic proportions. So when we say ARC-220 is one of a kind, we don't mean it lightly. We mean that in this time, at this distance, under these conditions, no other galaxy gives us such a pure, rich, dynamic view into the heart of cosmic transformation. It is a masterpiece forged in motion and fire, a galactic symphony still playing out, and the best stage the nearby universe can offer for observing what happens when galaxies collide and rebuild from their wreckage. Though ARC-220 has passed through the most violent phase of its galactic collision, the story is far from over. What we see now is not a static remnant, frozen in time, but a dynamic, reshaping system still undergoing profound transformation. Its chaotic interior is still in flux, its stars and black holes still responding to the gravitational echoes of the past. Even after hundreds of millions of years since the initial contact between the two galaxies, ARC-220 continues to evolve, steadily, and sometimes dramatically, in ways that will shape its fate for billions of years to come. At first glance, it might seem like the dust has settled. Two spiral galaxies have collided, ignited a starburst, and begun the long process of becoming one. But under the thick veil of dust and gas, gravitational instability, turbulence, and feedback continue to churn. One of the clearest signs of this ongoing evolution is the presence of the two distinct nuclei, still separated by 1,200 light-years. These galactic cores, dense with stars and possibly each harboring a supermassive black hole, are slowly spiraling toward each other through a process known as dynamical friction. Dynamical friction occurs when massive objects, like galactic cores or black holes, move through a sea of stars and dark matter, creating a gravitational wake behind them. This wake pulls back on the object, robbing it of momentum and causing it to gradually lose energy and sink toward the center. Over time, perhaps tens or hundreds of millions of years, the two nuclei of ARC-220 will merge completely, forming a single galactic core and potentially triggering a final, intense burst of star formation and black hole activity as the remaining gas is compressed in the final stages. Until then, the galaxy's core remains in a state of gravitational flux. Star clusters orbit erratically. Gas clouds fall inward along unstable paths, colliding, shocking, and sometimes stalling. This environment, far from being settled, is still violently dynamic, shaped by the residual motions of the merger and the feedback from ongoing star formation and supernova explosions. Every shockwave from a dying star, every gust of radiation from a new stellar cluster, reshapes the surrounding medium, pushing gas around and resetting the conditions for the next generation of stars. The dust, too, is in motion. Much of it, heated by intense radiation, is slowly dispersing outward, driven by powerful outflows that have been detected in submillimeter and radio wavelengths. These outflows, or galactic winds, carry away gas and dust from the central regions, sometimes at speeds of hundreds of kilometers per second. Over time, they will help clear out the central regions, allowing starlight to eventually shine through and potentially reducing the fuel available for further star formation. This feedback is critical in regulating the evolution of ARP-220. It ensures that the galaxy doesn't burn through all its gas at once and collapse under its own weight. And as the gas supply gradually diminishes, the nature of the galaxy will shift. Right now, ARP-220 is a starburst galaxy, actively forming stars at rates hundreds of times higher than the Milky Way. But starbursts don't last forever. Already, models suggest that the peak of star formation may have passed. The densest regions have likely exhausted much of their molecular gas, and while inflows and mergers may continue to stir the pot, the era of furious star birth is nearing its end. In the next few 100 million years, ARP-220 will likely settle into a new identity, a quiescent, massive elliptical galaxy, its star-forming days behind it, its structure relaxed into a smoother, rounder form. The tidal tails and distorted features will fade as stars spread out and gravitational interactions settle. The once bright nuclear starbursts will cool, and only the most massive, long-lived stars will remain shining in the central regions. This is the typical end state of many mergers between gas-rich spirals, the creation of a giant elliptical galaxy, red, dead, and quiet on the surface, but harboring a violent past in its core. One fascinating aspect of this transformation is the evolution of its stellar populations. Right now, ARP-220's central clusters are dominated by massive, short-lived stars, blue giants and supergiants that will soon go supernova. But over time, these stars will die off, leaving behind neutron stars, black holes, and white dwarfs. The remaining stellar population will shift toward lower-mass stars, long-lived red dwarfs, which will burn steadily for trillions of years. As the bright, hot stars vanish, the galaxy will grow redder and dimmer, moving on to the so-called red sequence of galactic evolution. The gravitational dance of the central black holes is also part of this long-term evolution. Once the two nuclei merge, their black holes, assuming each hosts one, will likely form a binary system, orbiting each other at high speed. As they spiral inward, they will emit gravitational waves, ripples in the fabric of space-time. Eventually, they will merge in a spectacular release of energy, perhaps detectable by future gravitational wave observatories. The merged black hole will be more massive and more powerful, potentially triggering low-level AGN activity, as gas continues to trickle in from the fading starburst. But the impact of ARP-220's evolution doesn't stop at its own boundaries. The winds and outflows generated during its starburst phase are already transporting metals, elements heavier than hydrogen and helium, into the surrounding halo and intergalactic space. This chemical enrichment will contribute to the broader ecosystem of the universe, providing the raw material for future generations of stars and planets in other systems. Even as ARP-220 settles into a quieter phase, its legacy will radiate outward, carried by the very elements its stars forged. In many ways, ARP-220 is a living record of cosmic transformation, a galaxy that is actively transitioning from one form to another, and one that we are lucky enough to witness while the process is still underway. Unlike ancient elliptical galaxies that finished their evolution billions of years ago, ARP-220 allows us to watch this metamorphosis in motion. Each new observation adds a piece to the puzzle: how galaxies grow, collide, form stars, blow out gas, and settle into new identities. The fact that we can study this evolution in such detail is a testament to our current observational power. Instruments like ALMA, the Hubble Space Telescope, the James Webb Space Telescope, and ground-based observatories across the electromagnetic spectrum are giving us real-time access to a galactic transformation that, until recently, we could only model in simulations. And because ARP-220 is relatively close, just 250 million light-years away, We can watch it at high resolution, see its structure evolve over time, and perhaps even observe changes in star formation rates or outflow properties across human timescales. Ultimately, ARP 220 is a story still unfolding. A tale that began with the collision of two spiral galaxies, igniting a firestorm of starburst and chaos, now continues as that chaos slowly recedes into order. It's the transformation from a storm to a stillness, from a furnace to a fossil, from the blazing noise of youth to the enduring silence of maturity. But in that transformation lies the blueprint of countless galaxies across the cosmos, and perhaps, the echoes of our own galaxy's distant future. ARP 220 is more than just a galaxy, it's a furnace of stars, a living monument to chaos and creation, a place where the universe exposes its most explosive processes in their rawest form. What began as the slow gravitational attraction between two spiral galaxies hundreds of millions of years ago has become one of the most intense and revealing laboratories in the cosmos, a galaxy on fire, both literally and figuratively. It is a story of collision and compression, of collapse and rebirth, of stars forming in brilliant clusters only to die in catastrophic detonations that reshape the very space around them. This is no ordinary galaxy. In ARP 220, the rules of galactic life are not merely followed, they are rewritten. It is not content with the quiet, methodical pace of spiral arms gently turning or stars forming at leisurely rates. Instead, it surges. It devours its own fuel with unrelenting hunger. It bursts stars in such dense concentrations that the boundaries between one stellar nursery and the next become indistinguishable. It has turned its central regions into a compact forge, where thousands of suns ignite in unison, only to die young and violently in supernovae that send shockwaves through already unstable clouds, triggering the birth of new stars in an endless cycle. But within this great cosmic furnace lies a deeper lesson, a glimpse into what galaxies truly are at their most primal level. ARP 220 is the universe with its mask ripped off. It is the inner machinery of galactic evolution exposed and laid bare, the gravitational gears grinding together, the feedback loops of star formation and supernovae locking in synchronization, the relentless march of black holes drawing ever closer, their gravity setting the stage for a final merger that may yet send gravitational waves echoing across the cosmos. It reminds us that galaxies are not static structures. They are stories in motion, each one with a past, present, and future shaped by collisions, interactions, and the ceaseless interplay between gas, stars, and gravity. ARP 220 shows us what that story looks like when it's turned up to its maximum volume, a moment in time when the processes that normally unfold over billions of years are compressed into a violent, feverish century of light and heat. And in this chaos, we see a kind of cosmic mirror. Because just as ARP 220 emerged from the union of two galaxies, so too will our own Milky Way eventually collide with Andromeda, creating a firestorm of its own. Though that event lies billions of years in the future, ARP 220 gives us a detailed preview of what such a merger might look like, how our familiar spiral arms might become twisted and torn, how gas clouds might crash together and spark waves of star formation, and how the black holes at the hearts of galaxies will dance, collide, and reshape their host. ARP 220 is also a bridge to the past, because the conditions we observe there today, dense molecular gas, rapid star formation, hidden black holes, mirror the environments of the very first massive galaxies that formed in the early universe. It allows astronomers to test theories of galactic growth, to validate simulations, and to decipher the physical laws that govern how galaxies are born, evolve, and ultimately settle into their final forms. It connects us not only to the future but also to the distant, dusty corridors of cosmic history. Even its silence is meaningful. Shrouded in thick veils of dust, ARP 220 hides its brilliance from visible light telescopes. But in the infrared, it blazes with unmatched intensity. It is a reminder that much of the universe's most energetic activity happens in the shadows, invisible to the human eye, and that only by listening carefully, by tuning our instruments to every frequency the cosmos emits, can we uncover the full spectrum of its story. And that story is still being written. Even now, new observations by the James Webb Space Telescope, ALMA, and other instruments are uncovering more detail, more depth, more questions. They peel back layer after layer of ARC 220's dusty veil, exposing the turbulent anatomy of a galaxy that refuses to settle, even as it drifts toward a quieter future. The full merger of its nuclei lies ahead. The final fate of its black holes remains unknown. Its legacy, etched in the stars it leaves behind and the elements it sends out into the universe, continues to unfold. In the end, ARC 220 is not just a galaxy to be studied. It is a cosmic event to be witnessed, a masterpiece of gravitational art sculpted by the rawest forces in nature. It is a blazing beacon of what happens when galaxies lose their structure but find their power. When the calm of orderly spiral arms gives way to the madness of mergers. When the universe decides, just for a moment, to compress hundreds of millions of years of cosmic evolution into a single, brilliant explosion of life, death, and transformation. It is a furnace of stars. A graveyard of giants. A cradle of chaos. And above all, it is a message from the cosmos, that even in destruction, there is creation. Even in the death of order, there is the birth of something new. And in galaxies like ARC 220, we find the most beautiful truths of all, that the universe is alive, evolving, and forever burning with the fire of its own becoming. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.